Good afternoon. It's an honor to talk to you guys. And I hope you'll enjoy it. Demian and I have a few things we'd like to talk about in the way of measurements, amplifiers and speakers, and that covers a lot of ground. We're each going to give a short PowerPoint presentation to begin with, just to get things going. We both realize that there's probably a pretty good diversity here of knowledge and experience. So some of you may find some of the slides a little too simple. Others may find some of the slides a little too much, but we'll work on the average as best we can. So I'd like to start, oh, by the way, one other thing is that after each one of the PowerPoints, we're going to have a couple of minutes for question and answer. If you possibly can, please hold your questions to the end of a PowerPoint presentation. So there'll be a short question and answer after the first PowerPoint presentation and another one after Demian's. And then after that, we are going to do some hands-on demonstration. So I will be demonstrating some amplifier measurements. Demian will be demonstrating some speaker measurements. And then after that, it will go really informal, and we may have an opportunity to answer more questions and also to measure some gear that people have brought here. So with that, I'd like to get started, unless there's any organizational questions up front.
Yeah.
Yeah?
Are you handing out notes, or should we be taking notes?
I believe the PowerPoints, I hope I'm not wrong, I believe the PowerPoints are going to be on the website.
Okay, fine. Thank you.
I hope that's right.
Plus a video.
Thank you.
Yes, that's right. The video is going to be.
So you get to see the first twice.
So I'm going to talk about amplifier measurement, something very dear to my heart, even since I was a teenager. I've always been fascinated by things like oscilloscopes, and signal generators, and stuff like that. And you know, if you don't get an electric shock that kills you from your vacuum tube amplifier, you kind of like to measure it. So, and along the way, I built a lot of my own measurement equipment because I just couldn't afford it. I was young. Where I worked, I had wonderful equipment that I lusted after, but I couldn't afford. Every once in a while, I could take something home. But when you spend some time actually trying to design your own test equipment, actually, it's quite a learning experience. You know, you always want your test equipment to be at least a little bit better than what you're testing, for example. And testing also helps you to understand cause and effect, what might be going wrong, things like that. So, you know, why do we measure an amplifier? That's the first thing I want to talk about. I'll just have one slide on that. We'll talk a little bit about traditional tests. What I mean by that is tests that you have commonly become aware of, looking at in stereophile over the years. A lot of those tests were carried out with analog equipment. Later on in the talk, we'll be demonstrating some more modern digital-based equipment. Beyond the traditional tests, I'd like to talk, at least touch on some additional tests that aren't quite as normal, but sometimes you want to have a test that really stresses an amplifier and makes it misbehave and torture it a little bit. I want to talk about some techniques that are good practices for doing testing where the testing you're doing doesn't necessarily disturb what you're testing. We'll talk about briefly touch on some traditional test equipment design, just how it works. Finally, we're going to talk about PC-based test equipment, and that's where the demo is going to come in. The world of PCs and A to Ds and digital signal processing has made a lot of this stuff much, much easier, less expensive, and more convenient. Finally, I'm going to say a couple of words about testing Class D amplifiers. They get more important every year, and they're also a different animal to test. So with that, I'll just get quickly started. I'll hopefully run through the slides fairly quickly. Why do we measure an amplifier? Is it for bragging rights? Maybe. But you know, as we go through the process of designing an amplifier, and let's assume that we're designing an amplifier that's ultimately going to be put into production, we have numerous steps. We're going to verify proper operation. We build the breadboard, it doesn't smoke, but we want to go a little further than that to verify that it's operating as expected. Nowadays, when you design an amplifier, you will almost always simulate it first using something like LT Spice. So when you get the amplifier working, you want to verify that it's behaving somewhat like the simulation predicted, with a good dose of skepticism, of course. You have to use some judgment there. So then, you know, that's part of the engineering development testing. Once you get the amplifier working and things look pretty, you know, pretty much within range, now you want to find ways where you can improve its performance. You want to discover things that are in the amplifier that may be constraining performance. So a lot of testing will help with that. A very interesting example of that is cell phone.
Sorry about that.
That's okay. One example of testing that comes to mind is one time I was testing a MOSFET power amplifier, and the distortion was not bad, but it was really higher than I thought it should be. It was like maybe 0.01, 0.02%. And I just knew that it wasn't supposed to be quite that high. To make a long story short, there was a parasitic oscillation burst that was happening on part of the waveform. And when I cured that, the distortion went into the 00 range. So that's an example of, you can find stuff that you weren't even expecting to find when you test. So it's not just so you can publish great numbers. Obviously, once you beat up the amplifier and test it and trying to improve its performance, that will lead to greater odds of having good listening results. Even though listening results versus test results is a very controversial subject, there is some correlation. I mean, and actually, sometimes there's even some negative correlation. For some reason, sometimes crappy amplifiers sound good to some people. I don't know why. But anyway, you really want to make sure that the amplifier is performing cleanly in every regard. That doesn't guarantee it's going to sound like the best amplifier on the earth, but it moves you in the direction of increased probability it's going to sound good. Finally, you get into production, you need to do production testing. That's somewhat of a different animal. We don't have to talk much about that. But basically, with production testing, you're not drilling down as far. You've already figured out the basic design. It's solid. But when you make up, 100 or 1,000 of these, you certainly want to uncover mistakes or bad components or something like that. So you want to devise fairly simple tests that are fairly quick, that will uncover bad behaviors that are not supposed to be happening in a well-designed unit. And finally, John Atkinson or somebody else at Stereophile may want to use some of this kind of test equipment to write their review. I love to watch or to look at all of the measurements he does, and those measurements tell a lot. So these are the traditional tests I was talking about, and they're almost in the order in which you might do them when you first bring up an amplifier. First thing you want to do is see where it clips, see if it blows up when it clips. You'll take a look at is because different amplifiers with different damping factors, putting it very simply, are going to have a different, slightly different frequency response as seen at the speaker when it's loaded with the variable impedance of the loudspeaker. This can make a big difference in the sound. This is especially an issue with vacuum tube amplifiers where we're having damping factors on the order of maybe 20, something like that. Solid state amplifiers, 100 on up is a typical number. We want to look at total harmonic distortion versus power and frequency. I'll have a couple more slides on that. We also want to look at the distortion as a function of different loading. Amplifiers do great when they're not feeding a load, but they're not doing much work. When you load an amplifier with an increasingly smaller load value, it has to pump out a lot more current for the same amount of voltage it's putting out. You'll get a lot more watts, but it's working very hard. Some amplifiers will just pretty much throw up their hands and crash if you try and drive 2 ohms. Many speakers, though, particularly with the issues of quoted speaker sensitivity and so on, many speakers dip down to a rather low value of impedance. Some people would say in these cases maybe the manufacturers are cheating a little bit. Maybe they call it an 8 ohm speaker, and who knows, maybe it dips down to 3 ohms at certain frequencies. And heaven knows how low some 4 ohm speakers might dip. So we have to be very aware of how the amplifier performs under those kinds of difficult resistive loads, and then of course we can also go to even more difficult inductive or capacitive loads. A couple of less well-known tests are, one of them is called SMPTE, Intermodulation Distortion. I'll have a slide on that. Basically, that one is looking to uncover the effect on the gain of a high frequency when it's in the presence of a low frequency. Because to first order, distortion is essentially the small signal gain of the device changing a little bit with the operating point. And so if you have a large low frequency signal moving the operating point around and you have a small little carrier sitting on top of it, you're going to get some amplitude modulation if you have distortion. So that's how that test works. CCIF is another one. I'll leave that to the slide. Frequency response, everybody knows what that is. Some amplifiers are better than others. You can see it's nice to get down certainly below 10 hertz for the 3 dB point, and even lower than that. You got to remember, when you have a system, you have a lot of components in series, and every one of those components has a low frequency corner. You add all of those low frequency corners together and you can end up with a much steeper and earlier low frequency roll-off than you expected. Now, one of the prime examples of unnecessary cascading of AC couplings, we'll call that, is just about any preamplifier you buy, the output is AC coupled. Almost any power amplifier you buy, the input is AC coupled. So here you've got, in a totally passive part of the system, 2 AC couplings in series, each of which is giving you some loss at low frequencies. There are ways around that. I'm not going to get into that now, but there are clever ways of getting rid of at least one of those. But anyway, that's why we want to have good frequency response. How good it is above 20 kilohertz is open to a lot of debate, which I'm not going to get into right now. Square wave response, that's another thing we like to take a quick look at. It tells us a lot. It tells us sort of visually how fast the amplifier is, just looking at it. This one is pretty fast. You're looking at a 10 kilohertz square wave. You can see that it rises very quickly when the polarity changes. It goes up and there's no overshoot. Now, this is better than it really needs to be. This is a very, very well-controlled, high-frequency performing amplifier. If you were to do this, by the way, at a large signal value, this is small signal square wave. If you do it at large signal, sometimes this slope is going to start bending over a little bit. And that means that the amplifier cannot move the volts any faster. That's slew rate limiting. That's also a rather controversial subject in terms of how much slew rate you really need. You'll hear this term bandied about, and later on, if need be, we can talk more about that. But right now, this is just the point I wanted to make. A square wave, you take a look at the square wave and you know a lot right away. You don't want to see too much ringing there. If your amplifier is unstable, or if it's on the verge of instability, you're going to see ringing at the top. You're not going to see it go up and around in a nice controlled way. When we talk about noise, there's a lot of different ways of measuring noise. But one of the most useful ways, and the way that the marketeers like the most, because it gives the best numbers, is A-weighted noise. And so, you know, one way to measure noise is you just measure it with a flat AC voltmeter with an oscillator going in. Maybe you'll measure from, you know, in a noise bandwidth of 20 kilohertz or 80 kilohertz. Remember, for those of you that are familiar with noise, the larger the bandwidth that you're measuring in, the more noise power you get. So if you're measuring unweighted noise, it really is only really meaningful when you say how big a bandwidth you're measuring that in. A lot of times you'll see in magazine reviews, if you're looking at unweighted noise, the measurement bandwidth will often be 80 kilohertz because that is also the corner frequency where traditional THD analyzers tend to cut off. But the A-weighting curve really is useful because, first of all, it's a very well-defined noise bandwidth. The equivalent noise bandwidth of an A-weighting curve is about 13 kilohertz. The other thing that A-weighting does for you is that it tends to cut out most of the hum. So you're really looking more at noise than hum. And there's very important differences between how you perceive hum and how you perceive noise. Sometimes noise really isn't all that terribly annoying. I used to love the sound of tape hiss in the morning, back in the day. But of course, the original idea behind the A-weighting curve was that it is supposed to reflect the way that we perceive the loudness of the noise. And of course, our hearing has a sweet spot up around 2 kilohertz. So that's why it's weighted more heavily up there. You will notice, by the way, if you look at a magazine review, if they spec A-weighted noise and unweighted noise, the unweighted noise number will not be as good as the weighted noise number. The difference depends on a lot of technical issues, but it'll be maybe 5 or 10 dB different. This is what I was talking about earlier about the importance of damping factor. What this is doing is just illustrating some typical things you might see. If you draw a damping factor as a function of frequency and realize that damping factor is it's the inverse of the output impedance compared to 8 ohms. So if the output impedance is 0.1 ohm at a given frequency, at that frequency the damping factor is 80. So you can see here, what I was talking about earlier is most tube amplifiers have a fairly low damping factor, and that does account for some of the difference in the sound. Certainly not all the difference, but it's something to certainly keep in mind. This is especially the case if the tube amplifier is driving a difficult speaker load. And some speaker loads, the guys that design speakers, to first order, all they care about is how their speaker sounds if it's driven by an ideal amplifier. So, you know, when they design their crossovers and this, that, and the other thing, they may not be caring a whole lot about the wildness of the impedance gyrations or gyrations or whatever it's going to be. And that'll obviously cause some effect on the frequency response as seen at the speaker terminals in use. Typical solid state amplifier in the middle there, and this is just, you know, they're all over the place, but it's not unusual to have a damping factor in a solid state amplifier of 100 or more in the midband. It'll usually go up as you go down in frequency. Some designs, if you look at that top one there, the damping factor on that one extends of about 300 out to quite a bit higher frequency. And in fact, for that amplifier, the output impedance is governed by the actual output coil that is usually there to control stability. So if you were to look at that amplifier ahead of that coil, if you could, you would even see a higher damping factor. At the lower frequencies, you're looking at actually some of the coil resistance. So that amplifier happens to have large bandwidth and a lot of feedback, a lot of gain. Here's just a very quick introduction to how you measure damping factor. There's a lot of ways to do it. One of the things we may talk about later is there's a different way to do it using these nice little red boxes from Quantasylum. But this is one of the traditional ways of measuring damping factor. You just take the amplifier under test, you drive it from another power amplifier, which could even be the other channel of a stereo amplifier. You drive it through an 8 ohm load with a known voltage, and you look at how much voltage you get at the output of the amplifier under test. That will allow you to know what the damping factor is. And of course, in a test like this, it's very easy to do damping factor versus frequency. This is what I was alluding to before about the effect of output impedance. If you draw a little resistor here, 0.4 ohms, call it Z out, that's the effective output impedance of that amplifier at some given frequency. You can see that that output impedance forms a voltage divider with the loading impedance that the speaker puts on. In this case, you can see that speaker is going from a low of 3 ohms to a high of 40 ohms. It's quite a wild variation. Most of that usually happens with a speaker in the bass frequencies, especially if you have a vented loudspeaker, you'll get a couple of humps there. But you can see in this example, we have an amplifier with a damping factor of 20, which is probably a tube amp. And you can see that that variation in speaker load impedance can cause a gain spread of over a dB. You can hear that. Some people can hear that. Another thing that crops up is total harmonic distortion versus total harmonic distortion plus noise. Now, in the old days, you almost always saw THD plus N, because the analyzers back then, the traditional analyzers, all they really did was they notched out the fundamental and measured whatever was left over. What was left over was the harmonics and the noise and maybe some hum too. So what happens is as the power level that you're measuring at goes down, the reference level that the THD is being spec'd to gets very small. Think about at 1/10 of a watt, the amount of room that you have for measurement without noise intrusion is pretty much all gone, right? The amplifier, first of all, if you look at this THD by itself curve, eventually at some point as you go down in power, the amplifier is really going to get damn linear and the THD is going to go way down. But what you used to see almost all the time in a magazine review or something like that, you would see THD plus N. So what you would see is this upper curve, and you could be tempted to say, darn, that amplifier's got a lot of crossover distortion, because we're all taught that crossover distortion is a distortion that gets worse as the signal amplitude goes down. And that is true to a point, but a lot of times what you were looking at there in the THD plus N review plot was the noise coming up and dominating the measurement. So it's important to distinguish between those kinds of measurements. Nowadays, with digital techniques, which we are going to demonstrate, using signal processing, digital signal processing, and fast Fourier transform, it's quite possible to separate out the THD completely from the noise. So nowadays you can act, and there's actually a button on this little red box that we'll talk about. You can pick to choose either one of those. You can plot either one of those curves. Here we have another plot that's quite useful. You've seen plots like this in magazine reviews. This is THD plus N versus power for an amplifier where we're measuring them at 1 kilohertz and 20 kilohertz. Now, those are the, in my mind at least, those are the two most important frequencies to care about. The third most important frequency, which I have not shown here, is a low frequency like 50 hertz. And by the way, a lot of people get very surprised when they measure 50 hertz distortion and it comes out to be higher than they thought, because if you know about amplifiers, it's usually easier for the amplifier to be linear at the lower frequencies because there's more feedback going on down there. But there's a little bit more to that in the real world. So, but in this case, what you're seeing is THD plus N, and you can see for both frequencies of operation, you're beginning to get noise. And I think this was supposed to be a dotted line. But anyway, you can see where the noise is starting to come up. Now, the reason the noise for the 20 kilohertz THD is quite a bit higher is because when we measure 20 kilohertz THD, we have to have a larger measurement bandwidth if we want to capture all of the harmonics. So you're talking about, well, in this case, I can tell you the measurement bandwidth was 200 kilohertz, so you could capture up to the 10th harmonic. Many distortion analyzers only go to 80 kilohertz. For 1 kilohertz, if you have the right kind of THD analyzer, it will automatically cut down the noise bandwidth so that it's still only capturing up to the, say, the 10th harmonic. In this case, now the noise bandwidth only has to be 10 kilohertz, so there's less noise. This, by the way, this is a MOSFET power amplifier, lateral MOSFET. And this is that same amplifier where we're looking at the behavior of the total harmonic distortion as a function of frequency. Here you see it for 3 different power levels, 1 watt, 10 watt, and 75 watts, all into an 8 ohm load. The amount of bias current is mentioned there because in MOSFET power amplifiers, the amount of bias current, how hot you run the output stage, plays a pretty good role in terms of what kind of distortion performance you're going to get. So here we see the other thing to know about amplifiers, and that is that they have a more difficult time of producing low distortion at higher frequencies because there's capacitances that have to be charged and discharged much more rapidly. That takes more current, and that causes you to enter more into the nonlinear operating regions of some of the different elements of the amplifier. But you can see this is not too bad. One thing that is kind of interesting is that, let's see, what do I want to show here? You see that the 10 watt and the 1 watt sort of trade places there a little bit. And some of that has to do with where we're getting into the crossover distortion region as a function of frequency. That's probably going into a little too much depth, but yeah, it's reasonably well behaved. And amplifiers, most amplifiers you're going to encounter, good amplifiers, are going to be in the range of 0.01 on down. Most consumer amplifiers are going to be between 0.01 and 0.1. But and audiophile amplifiers, quote unquote, they're going to be anywhere. You have no idea. And some of them will actually sound pretty good. Okay. I'm not going to go into detail here, but this is how a typical THD analyzer of traditional analog design worked. Basically, the guts of it is a filter. It's a state variable notch filter, which can be electronically tuned in terms of its center frequency and its gain. And basically all you do, there's a way of doing that automatically. All you do is you tune this to completely make the fundamental signal exactly the same as this fundamental component of that going in there. So if you make those exactly the same and you do that by auto-tune, you've canceled out the fundamental, you're left with the distortion components, and the rest of it you normalize the value so that the percentage is the proper percentage no matter what the amplitude level is, and then you just read it out on a meter or something like that. Another interesting thing is that you can see that there's a residual output there. When we talk about residual on a distortion analyzer, that means everything that's left over after we got rid of the fundamental. So that residual is going to show you the noise, the hum, and the harmonics. Now, if you really want to go to a sensitive situation where you want to be able to see low levels of distortion in the presence of noise, you can take that residual output and run it into a spectrum analyzer. And then you can really, really see down. The other thing that's nice to do is look at that residual on an oscilloscope. And on a well-designed amplifier, and I'm talking right now about a bipolar solid-state amplifier, most of the distortion is going to be in the output stage, and the most annoying part of that distortion is going to be crossover distortion. And you can actually, if you have a good amplifier and you look at that residual and you've notched it out well, you can actually see the little wiggle where the signal actually goes through zero. And it's very useful to look at that. On less well-designed amplifiers, you won't see that as well because there will be other nonlinearities that are, shall we say, bigger. I just pretty much described that. You can do other games where you can pre-cancel out some of the fundamental ahead of the distortion analyzer input to increase the amount of dynamic range you have available. You can play all kinds of games, but again, you want to look at whatever you can, and you can really, really get down to very, very low levels of distortion measurement capability by playing the right kind of games, notching out things ahead of the distortion analyzer and so on. I talked a little bit a moment ago about SMPTE IEM Distortion. That's Society of Motion Picture Television Engineers. That goes back to, gosh, 40s? Something at least.
Before that.
At least, yes. And the idea there is really quite simple. In fact, I think this was originally done to measure the distortion on film.
Yes.
Where it was photo...
Optical recording.
Optical recording, right. And the problem that they were trying to address was that the effective gain, end-to-end gain of the recording medium was a function of where you were on the operating point. So they said, all right, let's measure the gain of a high frequency, and we're going to measure that while we're tweaking it around with a larger low frequency. So the low frequency, its main job is to move the operating point around, up and down, up and down. And back in those days, distortion analyzers were not sophisticated, but this particular test was really easy to do with relatively unsophisticated circuitry, because there was a big difference in frequency between the aggressor signal and the victim signal. The victim signal is the high frequency, the carrier, the one that's getting screwed up by the big guy. So the big guy is 60 hertz. He's 4 times as big as the little guy, the carrier frequency at 7 kilohertz. You run it through the amplifier, and then to first order, all you do is you put an AM detector on the carrier, and voila, you have the distortion. Now, to do that, you need to do a little bit of filtering. You know, you need to get rid of the 60 hertz by a little bit of high passing and some notch filtering, and then you clean it up a little bit with a band pass around the carrier. Then you can finally detect it with a relatively ordinary AM detector. When they became more advanced, the IM analyzers were actually using what's called synchronous detection there, which had a tremendous noise advantage. And then after that, you filter it a little bit more and you read it out, and that gives you a pretty good idea of how that link in your playback system is operating. Most modern solid-state amplifiers, you barely see the SMPTE IM distortion, because for modern solid-state amplifiers, the 6 kilohertz or 7 kilohertz is still in a range where where a modern solid-state amplifier is very, very capable. So it's really not bothered as much by that big old 60 hertz signal as it was in the old days.
In the old days, it was a moving shutter. It was
Yeah.
mechanical.
That's right. Now, one of my favorite tests is CCIF. Here, we take 2 high-frequency signals, 19 kilohertz and 20 kilohertz, although for technical reasons, it's actually better to use 18.5 and 19.5 kilohertz. But basically, you're taking 2 high-frequency tones separated by like a kilohertz. And in the old days, again, we didn't have sophisticated stuff. Back in the really old days, we really didn't have much in the way of spectrum analyzers, in fact. So the beauty of this test, once again, was the stimulus frequencies were far different from the response frequency that we were looking for. So what you would get out of here in the old days, 19 and 20 kilohertz, you get the difference frequency, 1 kilohertz. That was easy to see, easy to filter out, easy to measure. Unfortunately, that 1 kilohertz component only tells you about second harmonic distortion. So in a fair context, CCIF, in my view, is only really useful nowadays if you do spectral analysis. And we'll get to that in a minute. In fact, we're going to get to it right now. This is what you'll see on a spectrum analyzer when you're measuring CCIF distortion. Now, the beauty of this is, first of all, the even order and the odd order guys are in different parts of the spectrum, so it's easy to distinguish. Once again, you see down here at 1 kilohertz, that's basically the measurement of second order distortion, like second harmonic, but this is intermodulation distortion. What's happening here is the 19 kilohertz and the 20 kilohertz large signals are interacting with each other, and they're producing all kinds of sum and difference products. Now, for odd order products, up here, what you're seeing here, first of all, F1 and F2 are the 19 and 20 kilohertz signals. On either side, you see a rather symmetrical looking spray of intermodulation products. And in fact, it's really kind of cool. It goes down at 18 kilohertz, you have the third, 17, you have the fifth, 16 kilohertz, you have the seventh. The most intrinsic beauty of this test is that the IM products, the distortion products you're looking for, are in band. It's going to be very important when we talk about Class D power amplifiers. But for now, you notice that you see distortion products on either side of that pair of tones. We don't really care that much about the ones on the top because in theory it's pretty much symmetrical. So this is what you'll see. John Atkinson, bless his heart, he shows these. He's one of the few people that does amplifier reviews that shows the CCIF spectrum. And this is the thing nowadays to really look at. Okay, the additional tests. Well, first of all, you want to bang the amplifier into clipping. See how it clips. That sine wave starts to get a flat top on it. But sometimes at the end of the flat top part, you get what's called sticking. And there's a number of things that can cause that, but one of the most obvious things is transistor saturation. Sometimes a transistor turns on really hard, takes time to turn it off. And so sometimes you'll see that flat top extended a little bit beyond where the sine wave should have come back into play, and then it'll jump back down. And that's commonly called sticking. I mentioned earlier slew rate. That's a large signal test where you want to see how fast the amplifier can make the signal change. It's quoted in volts per microsecond. So a crappy old op amp, like a 741, you were lucky to get 1 volt per microsecond. A good modern solid state power amplifier, you're going to get somewhere between 20 and typically 200 volts per microsecond. A good number for an amplifier in general, in my opinion, is about 50 volts per microsecond. Now, the reason you care about that reflects the margin that you have against high frequency distortion. This is just a first order argument. So it's certainly true that no music you're ever going to listen to is going to have a slew rate of 50 volts per microsecond. No problem. However, if an amplifier begins to get within range of that, its distortion will generally get worse. Now, back in the 70s, there was this big thing called transient intermodulation distortion, and it was used as an excuse for not liking negative feedback, and it turned out to be complete bullshit. But that's how it arrived. And in fact, it originally wasn't even, the moniker was a convenient sounding moniker, transient intermodulation distortion, but it was basically slewing induced distortion. Transient intermodulation distortion. So that was basically a reflection of amplifiers that did not have enough slew rate. When they get close to slew rate, think of it almost as if it's clipping in the time domain. It just can't go fast enough, going as fast as it can. Negative feedback stability, I touched on that earlier. You look at that square wave, you really don't want to see evidence of instability, which would be some little wiggles, ringing on top. Unfortunately, a lot of times, stability issues can be very, very subtle, and they won't just show up on a simple square wave thing. Sometimes if you take an amplifier and you run a high frequency sinusoid through it, and you run it up close to or at clipping, sometimes on the back side of that signal, as it's coming back down, you'll see a parasitic oscillation burst. And it's only there briefly. And it's because that instability depends on the operating point of the transistors. And if you have a perfect storm of operating points, your once stable amplifier may go into oscillation. By the way, I suspect that some amplifiers out there, even some probably good reputation amplifiers, may sound different because they are unknowingly going into some kind of a parasitic oscillation under certain conditions. Lots and lots of different conditions can be out there. Different speaker loads, different speaker cables. Amplifiers can be picky about capacitance, load capacitance. Sometimes you can trick them into oscillating with that. There are also some even more subtle effects that can come into play with some amplifiers. These effects, believe it or not, are transmission line effects. Now, we're not talking RF here, that's for sure. So you don't have to have your speaker cables have the characteristic impedance of your speaker. That's not what we're talking about. But what we are talking about is feedback stability. Feedback cares about what's going on in, let's say, the 500 kilohertz to 2 megahertz region. That's RF. And if you have 10-foot, 20-foot speaker cables, you look at that speaker cable, that number one, that is a transmission line. If you look at zip cord, like monster cable was 110 ohms, something like that, characteristic impedance, something like that. That's right. So if you look at the impedance that the amplifier sees looking into that speaker cable, what happens at the far end makes a big difference. The far end might be an open circuit. It might be a short circuit. It might be loaded with a resistive 8 ohm resistor. Who knows?
Or a loudspeaker as an inductor.
Absolutely. So the point here is that there's some really subtle effects that can come into play when the transmission line behavior of the speaker cable can be involved. But it has nothing to do with frequency response or time response. It has to do mainly with the amplifier's stability. Is the amplifier happy? And of course, one of the problems is that we all test our amplifiers on the bench with an 8 ohm load, 8 ohm resistive load. Those amplifiers, they're all happy, but in the real world, they may not be as happy. So it's just something to watch out for. Thermal stability. A lot of times, especially if you're operating it at the old FTC requirement of operating at 1/3 power into an 8 ohm load for 1 hour before you tested it, 1/3 power is roughly the place where the power dissipation in the amplifier is the highest, so it's going to get the hottest. Now, when an amplifier gets hot, the bias points change, and the amount of distortion that the output stage makes can be quite sensitive to the bias voltage or the bias current. So that's something to watch out for. One favorite test is to look at the total harmonic distortion of the amplifier as a function of time after you turn it on. Sometimes you will see the distortion go up and then it'll go down a little bit, and it may go up and down a little bit more. And that's because the bias conditions are changing because the heat sink temperature is changing. So this is another thing you want to look at when you're testing an amplifier. This is the scariest test, the short circuit test. Nobody ever wants to short an amplifier. You know, you've got this beautiful amplifier you built. You put the protection in there. You design the protection, but you're still scared to take that screwdriver and put it across the output terminals. Because if your protection doesn't work, you have magic smoke.
It's okay. The signal going through it, right?
Doesn't matter, either way. And this depends a little bit on the amplifier design. But you can, an amplifier can self-destruct if it's shorted, even if there's no signal going through it, because the feedback circuits will go basically open loop, and they can drive it right to the rails, and it'll try and put, 20 amps into your screwdriver. Now, some other amplifiers are remarkably tolerant of short circuits. Tube amplifiers typically are pretty tolerant of that. But anyway,
For that test, how long would you hold the short?
if the amplifier is going to blow, it's probably going to blow in a few milliseconds. And by the way, some of those big plastic packages that they have the output transistors in, when they go, they really go, they blow up, and you see all kinds of black crap from the destroyed plastic package. I mean, the thermals are really interesting, almost like a firecracker. You want to look at the line frequency harmonic spectra. There's 60 hertz everywhere. But some amplifiers are much, much cleaner in regard to not making hum and hum harmonics than others. So that's an important thing to look at.
You're talking the amplifier output?
Yes, yes. Testing with difficult loads. I think Damian's going to tell us a lot more about that, but we've already mentioned that there's some speakers out there that were designed without any regard to the difficulty of them being driven. They can really be difficult, and some of them are quite well known. EMI susceptibility, that's another thing. You know, you have all of these things about like power line conditioners and all that kind of stuff. A lot of times what's happening there, if it's happening at all, and half of this is probably snake oil, but if there is something happening, it's largely going to be susceptibility to electromagnetic interference from the power line. And actually with an amplifier, there are a lot of ways for EMI to penetrate the amplifier. The line is an obvious one. The input from your preamp is an obvious one, depending upon, say, what kind of interconnect you have. The speaker cables can be a wonderful antenna for EMI to be going right back into your amplifier. Think about this. That speaker, you know, at the end of your 10-foot speaker cable, the speaker is not grounded or anything. It's just floating around, right? And it's just inviting EMI to come in. So some amplifiers are much more immune to that than others.
Electrostatic speakers are worse because there's a power cord, so you have a loop.
That's right. That's right. And then other torture testing. One of the favorite ones is that you can take a big test amplifier and drive power back into the amplifier under test. Now, this is a little bit like the two-tone CCIF test, but envision this. If you want to make a torture test, let's say instead of 19 kilohertz and 20 kilohertz, we make it 19 hertz and 20 hertz. And we drive 20 hertz in the forward direction and 19 hertz in the backward direction at high power levels. What happens is, as these two test signals beat against each other, the amplifier output stage goes through virtually all of its combinations of operating point. So if there's going to be a safe area problem, this may very well stimulate it, or it may stimulate your protection circuit.
Or the magic smoke.
Or the magic smoke. I probably don't need to go into this. This is what a fake speaker looks like if you're going to simulate it on SPICE. This is a very simple one, by the way. Or if you want to build one. Sometimes people build speaker emulator circuits. The challenge with that is that inductor. You need a very good inductor that's capable of handling high current without saturating, although some speakers actually look like an inductor that's going to saturate. One other thing, though, related to this, here's a simulation of this circuit. This is a wake-up call as far as how much current can possibly go into a loudspeaker. It's a lot more in principle than the voltage, the sine wave voltage into 8 ohms. Because you can get, if you manufacture a particular kind of a waveform, you can get the momentum of the speaker cone to be acting like a generator, and you can then drive the signal in the opposite direction, so you almost have like maybe twice the effective voltage across that the resistance of the voice coil. So this is not going to happen in the real world, but it is an interesting thing to observe that speakers are not completely benign in terms of the way they load an amplifier and in terms of the amount of current requirements that they can take from an amplifier. This I just talked about. I should have talked about this, put this slide up earlier. This is fairly obvious stuff. If you're looking at a high impedance node, you're working on an amplifier, you're on your bench, you really don't want to load a high impedance node to the point where you interfere with the nominal operation. In particular, you like, let's say you want to measure the voltage at a node. You put your Radio Shack DVM on there, right? You put the probe on there. Well, that probe's got capacitance. And you may very well have that capacitance cause the amplifier to go into oscillation. So that's something to watch out for. I often put a 1K resistor right in series with the tip of my voltmeter probe, so that pretty much keeps me away from that danger zone. Obviously with scopes you want to use 10 times probes. Ground is not always ground. And we could have a whole day about grounding. Grounding is a difficult subject for anybody. Even when you know, there's some people that would love to believe that if you design your circuit board with a ground plane, ground is always ground. Not true. Ground planes are very imperfect as well. So think about that. Ground loops, they kill us all the time. Your test equipment, the safety ground that you have all your meters hooked up, they're all plugged in, they all have the IEC connector with the safety ground in them. Boy, do you have a bunch of ground loops there. It's terrible. Sometimes you just want to cut that safety ground and take a chance. Just make sure one of them isn't cut. Finally, keep in mind, compact fluorescent lights and LEDs have switching power supplies in them. They are noisy. The house that I live in came with all LED lights, which I thought was great. It's a fairly new house, Energy Star, all that. Those damn LED lights make a lot of electrical noise. And so if I'm testing something that's sensitive, I turn off all the lights and turn on a couple of good old incandescent lights. It makes a huge difference. You can see it right on the scope.
Can you see that noise on your domestic supply in your home? So, I mean,
Oh yeah, yeah. Oh, it's everywhere. Yeah. Okay, so the traditional test equipment, you want to have audio signal generator, scope, voltmeter, harmonic distortion analyzer. These go up in price, right? And spectrum analyzer. And most of this stuff in the old days, you know, it was good. Analog circuits, Tektronix, Hewlett-Packard. Nowadays, things are a little different because of the availability of things like D-to-A converters and digital signal processing. And we're going to talk about that in a second. But this is the stuff that was very, very much in vogue, at least to the end of the 80s. Probably quite a bit further than that. Now we're into the 90s and the 2000s. PC-based test equipment has really come into vogue. And the reason is pretty simple. First of all, processing is now cheap. Digital signal processing is cheap. You don't need a digital signal processor chip to do most digital signal processing. You can do it in an Intel CPU. They're that fast. The other thing is that your PC is your user interface. You know, you don't have to have the expense of all of these knobs and all that stuff you had in the old days. Now it's all right on your screen. Now there's two rough classes that I would like to describe here. The first one is based on sound cards. And I think Damian's going to talk a little bit about sound cards. But basically, it's a sound card that's connected to the PC, and there's some software inside the PC that does your analysis for you. And it works pretty well, actually. But then you also have dedicated hardware. Now, the dedicated hardware is a little bit more turnkey. And this is what we're going to be describing a little bit later. These boxes are made by Quantasylum. And this box on the bottom here is basically your modern day distortion analyzer and more. $450. It's a deal. You couldn't do this for $20,000 20 years ago. So, and the heart of it is an analog to digital converter, a digital to analog converter, and some digital signal processing. Some of it goes on in here, some of it goes on in your computer. It's powered by a USB interface back to the computer. So that's a very, very nice, very convenient piece of test equipment. Is it perfect? No. The best A to D converters and D to A converters for audio use, which are pretty much the same as used in there, they can sample at maybe 192 kilohertz, 24 bits. That's pretty good. But in terms of your being able to measure things, you can only measure up to, theoretically, half the sampling rate. So in this box, for example, you can get decent measurements up to about 80 kilohertz, which is very good. The only trouble with that is, and this is, just the way life is, what if you want to measure total harmonic distortion at 20 kilohertz? Well, the fourth harmonic is already 80 kilohertz. And the fourth harmonic usually isn't the biggest area of concern. Even harmonics aren't as bad as odd. You would really, really, really like to see at least to the fifth harmonic. Can't do that with 192 kilohertz sampling. So there are limitations in the real world, and the more traditional THD analyzers did in fact have a much wider bandwidth capability, so you could see out to the 10th harmonic. As I mentioned, these boxes make heavy use of the fast Fourier transform. That's pretty much their bread and butter of how they do it. It's just a mathematical process that is done on the digital data, and it can give you spectral information. We'll be demonstrating some of that as well. Finally, digital storage scopes are made very nicely these days. I think you brought a picoscope, right?
There.
And what's the bandwidth on this
That's
picoscope?
at 200 megahertz.
And it's what, 2 channels?
2 channels, yeah.
Isn't that something? 200 megahertz digital storage oscilloscope. And what is this? Less than $1,000?
I think that was around, new price was around 700 or 800.
There you go.
You can spend a lot more, but they also
Right.
have cheaper ones.
But this is the power of PC-based test equipment nowadays. We've already pretty much covered that. You have a sound card. You do have to interface it carefully. Pete Millett has a great design that many people have used and built that performs basically this function. It protects your sound card from overload. It allows you to scale the signal levels, things like that. Now, this is just a picture of this guy right down here. I'm going to say a couple of quick words about it. The QuantAsylum QA401. I'm a big fan of this part. You can go to quantasylum.com. There's all kinds of nice little red boxes that Matt Taylor makes, and they're very, very reasonably priced. They're well engineered. They're very convenient to use. It's just a great getting started tool. Many of us older guys have racks and racks and racks of old, heavy HP Tektronix gear that we probably bought on eBay, stuff that used to be the top of the world back in the 70s and 80s. But this does a lot of that now, and it's new. So anyway, this is what it does for you. Economical PC-based measurement system, a simple, straightforward USB interface. It's very turnkey in terms of setup and the user interface. One of the things with sound cards is sometimes there's an amplitude calibration issue, if I'm not mistaken. This is all taken care of for you automatically in this dedicated piece of equipment. It's purpose-built electronic test equipment. And among other things, it'll measure THD, THD plus N, frequency response, signal to noise. It'll show you the FFT spectrum and a whole lot of other things. Finally, Class D amplifiers, a whole new brand, whole new beast. They operate differently than linear amplifiers. Class D basically is a pulse width modulated waveform that is a representation of the signal, and to first order, that output, that raw output, is going from rail to rail. It's a square wave at a frequency and pulse density or pulse width that varies, and that's how it makes the signal. The average value of that very high amplitude square wave is what your signal is. Now, of course, at the output of the Class D amplifier, they put in some filtering, and that's where the good news and the bad news is. They have to filter that crap out, and it's hard. A lot of times the carrier frequency is in the vicinity of 500 kilohertz, maybe half that, maybe double that. But this starts out as a very, very large signal. And it is going to, first of all, it's going to disturb the distortion analyzer, the sensitive inputs of the distortion analyzer, those op amps at the front end. If they see too much of this high frequency garbage, they're going to slew rate limit or do some other bad thing. But one of the other things I wanted to mention is that because Class D amplifiers are so fundamentally different, they also behave or misbehave in different ways. This is something that designers are still getting used to. We can't rely on some of the traditional measurements that we did. Total harmonic distortion at high frequencies like THD20, useless. The harmonics are filtered out by the filter. So you can actually, and I've seen reviews where the THD, oh, it's going down at the higher frequency. Not. So here's where that CCIF test that I told you about comes in. Because the distortion components of that test lie in band, now, even with a Class D amplifier, with its output filter, you're going to be able to see those components. So if you ever look at a review on a Class D amplifier, don't even look at the THD unless it's THD1. Look, if it's shown, look at the CCIF and see how much those spikes are. That's where the action is. As I mentioned earlier, the high frequency output disturbs a sensitive THD analyzer. Because of that, you need very, very steep output filtering. There's a filter called the AES-17 filter, which is basically a brick wall filter between 20 kilohertz and 24 kilohertz. It goes from like, I don't know, 1/10 of a dB down to like 60 dB down over that 4 kilohertz range. So that's a really, really, really steep brick wall filter. And the idea of that is to get rid of that carrier frequency so you can measure very, very low values of distortion in the presence of that. And the need to measure very low values of distortion in Class D amplifiers is a reflection of the fact that they've gotten much, much better over the last 10 to 15 years. So we are now in the range of, we want to be able to see 0.01% distortion on a Class D amplifier, and maybe less. If you do the numbers, you have to filter the crap out of that to get that, to be able to distinguish that distortion from the noise caused by the carrier. There's also new distortion phenomena in Class D amplifiers. They have terrible, well, some of them do. Power supply rejection is a problem in Class D amplifiers. That rail-to-rail thing that's representing the signal, well, when we say rail, we mean rail. That rail's going all over the place. It's got power supply ripple on it, all kinds of crap. So that's going to make its way into the signal. Now, that's a highly oversimplified description, but that is one of the big problems that Class D amplifiers face. Some of them do a very good job of addressing that problem. Others just don't. Another one is that a Class D amplifier is sort of like a switching power supply, and in some switching power supplies, they can operate in either direction. So if there's energy going back into the output of that power supply, that switching power supply will transfer that energy back to the source. Now, when you're amplifying an audio signal at very low frequencies, and that signal is asymmetric, and you have plus and minus rails, if you're sucking a lot of current out of the plus rail and then that changes, some of that energy gets transferred back to the other rail and actually tries to elevate that rail. You're pumping energy into the other rail. That causes all kinds of trouble. And in fact, if you keep in mind that the amplifier has poor power supply rejection, it's easy to see why that would cause all kinds of bad things to happen. So that's pretty much it. There's an example of the kind of filtering you have to do. Sometimes, this is sort of like an audio precision, very simplified version of an audio precision setup. They actually sell a separate pre-filter. This guy right here, he's the one that takes the brunt of the punishment of that huge, big signal. And a big portion of him needs to be passive. Because again, if you make it with active parts, you've got the same old problem, right? So yeah, and if you build that with passive components and you make it a complicated filter where you need inductors, guess what? You need really darn good inductors. So that piece right there can be very expensive. In the earlier days, the AES 17 filter that I talked about, which is the real brick wall, nowadays that's inside the signal chain in the AP, and in the newer APs it's done in the digital domain. But that filter in the earlier days, that was the only filter that was used. They hadn't come along with the pre-filter at that point. But the AES 17 filter, which is a 9th order elliptic filter, had to be implemented totally passively with the most expensive inductors you could imagine. And it was very, very, very expensive and difficult. Nowadays, it's a little bit better, but this is a big, big thing you have to watch out for testing Class D amplifiers. And that's it. Thank you very much. I apologize, I've probably run over a little bit, so just a couple of quick questions, and then we should move on to Damian's talk. Yes?
But why do we even care about the second harmonic of 20 kilohertz? I mean, surely that's outside of our hearing range.
You're exactly right. Why do we care? We can't hear. I don't know about you, but I can't even hear 20 kilohertz. Here's the thing we always have to remember, that harmonic distortion, and all these other distortions, they are indicators of something. They're indicators of nonlinearity. It's not that you're hearing the harmonic. In some conditions, in music you may hear the harmonics, but when you're testing an amplifier, the harmonic content is symptomatic of the nonlinearity in the amplifier. So for example, you're never listening to just a sine wave, right? If you were listening to a sine wave, it might make a little bit of sense to say, well, I can hear 40 kilohertz, the second harmonic, but in reality, what you're hearing distortion-wise is the distortion created by a highly complex waveform like music. And so there's spectra all over the place. And we have a nonlinearity. All that spectra is interacting and producing other spectral components. So the thing to remember with any of these distortion metrics is that's all they are. They're just metrics. They're indicators of the presence of a nonlinearity. Just like when you go to the doctor and they take, they look to see if you're sick, they look for antibodies, right? The antibodies are not what your sickness is. The antibodies are a symptom of what's going on in your body. They're a symptom of your body fighting the infection, right? So think of it that way. These distortion measurements are not really measuring what you're hearing. they're measuring an indice of nonlinearity. Yeah.
In terms of PC-based measurement devices, they've improved quite a bit in a very short period of time. What's the likelihood that they're going to keep improving at that pace so that buying them means they're outdated in 6 months?
Oh, there's really two questions there. Well, the second question was one of obsolescence.
Right.
And that's always going to be a continuing issue with virtually any electronic
But I
equipment.
was wondering if there's a pretty steep curve where they're improving the equipment rapidly.
You
or
know,
some of it's stable and that's the way it's going to
I
be.
think it's not improving rapidly, in my opinion, at this point. The limiting factor is basically your A to D and D to A converters. And, you know, they will improve, that's for sure. But 192 kilohertz sampling at 24 bits is, you know, pretty much the norm nowadays of the high end. There are some 384s. I don't think there's very much in the way of consumer.
Actually, the converter in here will do 768, but its performance is degraded, so that's why it stopped at 192.
Okay, there you go. How many bits is it at 768?
Problem is it rolls off about 7 or 8 dB by the time you're there.
Oh, okay, okay.
So rather than work
Right.
around with it, just roll it
That's
off.
right.
Plus, how much stuff can you
Right.
really make use of?
So anyway, yeah, it's definitely going to improve, but the rate of
What's
improvement.
available today will remain
Oh,
good
it'll
enough
be
for the testing
absolutely,
work.
absolutely, yes.
Relating to that question, I've looked at a lot of sound card-based test systems, and they don't specify the low end, I mean, the bottom end on anything. Where's the floor? Like the noise floor and, you know, all of that stuff. How does that compare to something like, you know, an HP audio analyzer versus, if you can afford an audio spectrum analyzer? You go to the data sheet, you can see what the floors are on those
Right.
things.
Right.
But this sound card stuff, I don't know if it's a toy or if it's real.
It's both, actually. First of all, the sound cards, they weren't designed to be a measurement instrument. There's a few of them out there that really are focused on that, and I'm certainly not an expert on which ones are that way. But your point is very well taken. And my answer to that is get one of these.
So these are respectable.
Oh, absolutely.
Okay.
This box is, I would say, it's better than most sound
You have to
cards.
spend probably $700 or $800 for a sound card with similar performance.
Right.
Well, I could buy a sound card for $800 too. That doesn't mean it's good.
That's true too. That's true too. And
Actually,
with the sound card, you have to buy the software on
Right.
top of that.
Right.
Here, $450, you're good to go. You know, you get this thing from Amazon at your doorstep, and in less than an hour or two,
Okay.
you're on the air. You know, and you can do a loop back, input to output, and you can see how good it is. And it's really remarkably good for the cost and given the amount of convenience.
One
Yeah.
again, a related question. How do these things compare to like the old the solid state HP audio analyzers that you can buy, or some of the older, you know, the eBay stuff?
Sure, sure.
The stuff you and I probably have.
Yeah. I have a vintage HP 339A.
Yeah.
It's a nicely executed piece of equipment, but it can't do as well as this.
Oh, okay. So these are actually surpass those.
That's right.
Okay.
For the most
Yes.
part.
So you, on one of those graphs, you showed 400 milliamps or so of bias current in
Right.
the amplifier. How many devices in parallel was that spread over?
That was two output pair. So each transistor was operating at a bias current of 200 milliamps, which, by the way, is a little on the high end for it's running. That was a Hafler modified amplifier. So
So you had to crank up the bias to overcome the drive issues.
well, no, not particularly, because it was not a Hafler. It wasn't a Hafler design card. It was my design card in the Hafler environment. But with MOSFETs, the beautiful thing about MOSFETs is that the more bias you give them, the happier they are with distortion. Bipolars are the opposite. Bipolars are, you can move the bias up too much or down too much, and the distortion will change. The crossover distortion will change. The MOSFETs, you start out typically with more crossover distortion, but it's softer crossover distortion. And the more bias current you give it, the less distortion you're going to have. Obviously, there's a limit to that. Yes, Paul, we're done. Thank you.
Okay. Now that you know how to measure amplifiers and can make them all absolutely perfect, let's go dive into how to measure speakers. And that means finding the right tape measure, right? Okay. Remember, they can't exist in isolation. That amplifier may be wonderful on a load resistor, but without a speaker, it's kind of an object. And again, the speaker is kind of useless unless it's hooked to an amplifier because it won't make any sounds. So we really want to get them all together. The other few points, the traditional loudspeaker with a passive crossover and so forth, it is the realm of a kind of a specialty marketplace today. All of the real work on advanced speaker stuff is happening in Asia for the most part, because all of the manufacturers of speaker parts went to Asia, because that's where the business is. And there today, the volume is in small speakers, electronic crossovers, all done digitally, all very sophisticated products done by shops which are not very sophisticated in listening to their products. They meet specs and then they ship them out. Any of you who've ever listened to something like an Amazon speaker know where the world is at today. It's not very exciting, but that's what we have to work with. Fortunately, we have all this marvelous technology to support it going forward. So what I'm going to try and do here is cover measuring speakers so you can learn how to do it. You can go measure speakers and then you can go develop what you want out of it. Next thing, why do you want to measure it? If you have a perfectly good sounding speaker and you don't notice any problems, are you measuring it so you can go find problems to fix? Or do you have questions about whether it's really working right? That's why you have to figure out what you're going to measure and why, because there's so many things you can measure. One thing that's different about an amplifier and a speaker, an amplifier lives in barely 2 dimensions. You got a voltage and you have time. That translates into all the things that we were measuring there. Speakers live in almost 4 dimensions. They have sound pressure in multiple places in multiple time, and we also find that the signal you put in comes out at multiple times. It doesn't necessarily come out all at once in one nice clean signal. And this is the stuff you're measuring for to try and make it better. The problems that you would be looking for, traditionally, you want to get the frequency response right. And we'll go into a few details about things to watch for and understand in measuring frequency response. Distortion. There is some things you can do about it in a speaker, and there's some things you're probably not going to be able to fix. If you're not designing drivers, you have what the driver is. You're not going to make a new driver. And the old days, I remember painting glop on drivers to make them better. Forget about it.
Painting, what's it?
Pardon me?
Is that painting dope? Doping?
Yeah.
All right.
Yeah, nobody does that anymore, I don't think. You can do it if you really know what you're doing, but otherwise you're just going to wreck the speaker.
I nearly did that recently. Thanks for the warning.
The other things you want to watch for, driver compression. The reality is, particularly in woofers, when you go up 10 dB in input, you don't necessarily get 10 dB more output. And some speakers and some kinds of horn designs, you can actually get more than 10 dB out with a 10 dB increase. But typically, like with a woofer, for a variety of reasons, you put in a 10 dB increase, you get a 9 dB increase in the output. And those are things that you really can hear, and you want to understand it and understand if you have an issue there and what you can do about it. The other classic thing that you're going to test for is, usually you can hear it, but sometimes you can't necessarily, is rub and buzz. In production, this is really important. If you have 100 speakers that you have to test in an hour, you want to find a way to find the loose particles inside or if the voice coil is rubbing. In your case, you want to be able to test the driver, make sure it's working properly, probably break it in before you even assemble a speaker, and you want to know if it's got a problem. And then, again, rub and buzz, something loose inside, the driver's banging on the wiring, all those things, and they all happen in the real world. This is sort of a breakdown of a driver and showing you all the places that something can go wrong. You can have all of the voice coil can be misaligned in two ways. It can be not centered so it rubs. It can be not centered so it goes further drive in one direction than the other, and that translates into a very distinct kind of distortion. Again, I mentioned something banging on the back of the cone because the flex lines, you have the voice coil. There are wires that come out of it. They're called flex lines in the industry. They're made out of a kind of special tinsel wire, but they can hit the back of the cone, and under some conditions you'll hear a little ticking sound. They can be wired up backwards. You don't know that until you've checked it. And depending upon the driver and who's making them and how many they're making, it could be one extreme or another. The surrounds and all of that, they could be not quite ideal. A classic problem is the surround is re-radiating. It always is, but because it's too soft for the size of the box you have, it starts canceling out the signal that's coming off the cone. These are all things that you will be looking for. And as I mentioned, loose stuff under the dome. It's really frustrating when you have the speaker and you shake it and something under the dome is rattling. You can't get at it to fix it. And the spider, one of the classic tests that I used to do, it's better today than it was, is that we would take a speaker, put it on a bench, drive it with 5 hertz from stop to stop, and just leave it running overnight. Early on, you'd find that the spider would just disintegrate by the morning. They got much better, and the reason they're better is the car audio industry couldn't tolerate that. You can't make the windows pop out if it does that. So these are the things that we would be testing for, and I'll try and see how much of this we can quickly test, demonstrate how to test for, and what you need to know to do it. There's frequency response again, distortion, noises, which are actually a bigger issue than distortion typically. Getting the polarity right. Is the driver as sensitive as they promised? Is it what you need it to be? And this goes back to the problem of measurement. If it were like an amplifier, you got 2 leads there, you can go measure voltage, you can measure frequency response, distortion, all manner of things off of those 2 leads. You multiply it in a loudspeaker, you're measuring it on axis, off axis, and all manner of things to measure both amplitude related and frequency related. Typically, frequency response, as I said, it changes with level. It's intrinsically going to change to some degree with level because it's a motor that's not 100% efficient. Then you have the compression issue, and as I said, which angle. The nature of the driver will influence which angle gets what response. I did measure some years ago a very highly rated speaker from Germany. On axis, it was quite wonderful. Off axis, it was really bad. At 90 degrees, it was wonderful again, which is absolutely not what you want in a real world room. Okay, distortion. Classically, we measure the 2nd and the 3rd harmonics because that'll tell us pretty quickly. You'll do a frequency sweep, a distortion sweep, and it tells you how the driver is behaving in terms of distortion versus frequency. And again, you can do that at different levels until you burn up the driver. And then we'll get into delayed resonances, also called stored energy and all that kind of stuff. And then there's also, I mean, I'm talking here about acoustic measurements. There's also the fact that you need to do the electrical measurements of the driver so you can characterize it. You can do teal small values out of that and then go put them into your simulation software, figure out if you've got the right size box optimized, and then build the box and find it doesn't work the same. Okay, acoustic test environment. If you're going to test a speaker, ideally you either want an anechoic chamber. That's that thing over in the corner. Trust me, it's very expensive and it doesn't go down very far. No matter how big you think it is, you spent so much money on it and it still only goes down to 100 hertz. So that's not necessarily where you need to be, and today you don't really even need that. The best technology I know of today for measuring a speaker is what's called ground plane measurement. We'll get into a little more detail, but it's fairly easy to do if you have an open space. You can do it in a parking lot. You might even be able to successfully do it in your driveway. I had great success in the back of a warehouse. It was wonderful because everything was about 30 to 40 feet away. I can measure to below 20 hertz with it. And then there's the real world that we normally live with, which is essentially what's right here. You have a speaker and a microphone and some distance, and then I'll show you all of the things that are going to screw you up, and we'll learn what we can learn from it. Anechoic construction. As I said, you don't want to struggle with this. I read something about a low-cost anechoic chamber that was $5,000. That was in 1960. Yeah, today you're going to spend hundreds of thousands of dollars to get there. This is more about a ground plane measurement. You have a speaker, you have a microphone, 6 feet away from it, and there's reasons why that works out really well. And it's a fairly simple thing to set up. But the point here is that you have to have all of the reflecting surfaces, whether it's a wall, a ceiling, or even a post. Those have to be far enough away to get down to the low frequency limit you want to get to. So in this room, well, the carpet is a problem. You need a hard surface. Concrete floor is great. The reflections are what you want to get away from. And here, let me go see if I can help a little bit with this. As you can see, you have the direct signal down there from the speaker to the microphone. Then you have a reflection off the ceiling, and then you have another set of reflections. Those reflections will degrade the quality of your measurement. In some cases, they can actually dominate the measurement. What you see here in the picture, if you can see it, that yellow area with a bright, long spike, that is the initial signal coming from the speaker. You can see the high frequencies are quite clear. Where it switches to white, that is the first reflection. That, if you can window it, eliminate that, then you actually have a measurement of the speaker. Once you include that, things get different. Yeah, this is what we actually typically have to work with because we don't have access to a nice large space. And we'll go into what you can learn there. Equipment. That slide in the picture in the middle, that's the old days. And that, what you see there, cost a fortune. That was Macintosh in the 70s. Today, as you can see up in the corner, that's an Omni mic. That's a very available, around I think $350. You get the microphone, the software. It's very like the Quantasylum. You plug it in and you go. The other option over here, this is what you would buy today. This is Listen. It'll set you back, it's almost like $5,000 a year to use it. It can do a whole lot of things, but that's for production for somebody who's got deep pockets. Okay, we have dedicated systems. There are a bunch of them out there. At the pro level, Listen, Audio Precision, they have solutions. You can get a Clio system. These are all packaged systems. They take care of everything from end to end. You provide a computer and you're on the air. Clio is another one. They've now migrated. The current version uses a USB interface. Before that, they went through several generations. And I believe they have an upgrade path if you have one. I hope so. You can also get the Clio Pocket, which is a small solution. It's a subset of what Clio can do. But again, it's packaged. You buy it. You can turn it on and go. Praxis has been discontinued for a number of years, but I've been using it forever, and it has a lot of capabilities. I'd recommend it if you're willing to learn how to use it. The Omni mic, which we touched on briefly, and we actually have one here, and we can learn how it works. It again is designed for the hobbyist who doesn't want to learn a whole lot of stuff that's very specific to doing it, just wants to get measurements and get useful ones. Quantasylum is developing acoustic software for their box, but that's really production oriented. It's not so much something that you can use to develop a speaker. The more typical solutions that us mortals would be using is software from somebody like Arda or REW, which started out as a way to tune your room. And there's a bunch of others like that. And then you match that up with a microphone, either the mini DSP U mic is a USB microphone that you can get a calibration file with, or you can get one from Dayton Audio with a calibration file. And there are a bunch of similar products. The Dayton Audio, I mean, there's a guy in, I think he's in Taiwan, who's making all of those very similar little microphones for everybody. And the difference is whether somebody did QA on it or not. So you'll pay anywhere from 50 to 100 bucks for it. But any of those will work. The calibration file is important because then you'll know much better what you actually have. Okay, and again, it's kind of a repeat of the past. The Omni mic, Clio Pocket, the U mic plus the REW is kind of a package that you can get, turn on, and you can start getting useful information. Otherwise, you get the software, you go get the necessary hardware to turn it on. There's a handful, there's a whole bunch of other stuff, and there are a number of people that we see less in our channels here, but in Europe and in Asia making similar software package that you use with a reasonably high quality quasi-pro sound card. This won't necessarily work with a sound card that's built into your laptop, but if you get something like the little Focusrite USB sound cards or any of a number of similar ones, they're perfectly adequate for doing all of these measurements. Now, one key thing before we get into this, if you're using one of those sound cards, make sure you turn off the effects. You have to go in and make sure none of them are on, or you'll be basically mapping the effects to speaker tuning. Okay, measurement microphones. They are different from a recording microphone or a typical microphone. They are designed to have a particular quality of frequency response, directional qualities, and all of that. It's defined, it's specific, and ideally you have a calibration file that somebody has done that tells you exactly what to expect. Now, there is a number of key surprises. Let's see. Like, here are 3 different measurement microphones. One is a B&K 4135, really expensive. It's a 1/4 inch microphone. It measures out to 100 kilohertz. The Natty, I picked this up used off of eBay for 25 bucks, knew they were around 50 bucks. It looks like it's almost the same. And the Giardin, which is that little thing over there, is essentially a Panasonic capsule glued to the end of a chunk of brass tubing. And it works really well. So all of these are possible. You can build those. The Linkwitz site has directions on how to build something very like that. So there's lots of options there. Now, here's the reality of these 3. Okay, instead of looking at the center part with low resolution, this is a high resolution measurement. All of those wiggles are because it's not in an ideal place and there's reflections. The reflections affect it all the way up to the top end. This is measuring out to 35 kilohertz. I did this with a Pioneer Ribbon tweeter because it's one of the few devices I could find that has any response up to there that's useful. And this shows you that the B&K characterized it out to 35 kilohertz. The Giardin actually measured accurately out to there with its calibration file. The Natty, without a calibration, you see the roll-off there. That's because you need a calibration file to tell you that it's rolling off. But those dimensions are pretty small. It's not worth worrying about for most things, and very, very few drivers actually make it to 30 kilohertz. So just don't worry too much about that. And it's really hard to measure high frequencies because you move the microphone a half an inch, everything changes. Okay, next thing, on axis versus the off axis. And I got a little concerned about this because I saw recommendations in one software. You take the microphone, you point it at the ceiling, and then you go do all of your measurements, right? Well, that difference between being straight on axis and being at right angles there at the microphone nominal thing. This is a 1-inch microphone. At 1-inch microphone at 10, 12 kilohertz, you get basically a 6 dB difference between on axis and at 90 degrees. That's not insignificant. And if you aren't aware of this and you just sail on, what you'll do is end up with all of the tweeters cranked way up. And if you start getting used to that, then everything sounds rolled off. But that's not right. And here's what's happening. We can get deep into this, but basically, if you have a cylinder in free space pointed at something, and you have a sound wave coming at it, the sound wave builds up on the front of the cylinder. At the point where the wavelength of the sound, in this case, the wavelength of the sound matches the diameter of the cylinder, you'll get a 6 dB boost. And then when you double that frequency, it's 2, it actually has a notch effect. So that's why this whole thing about getting the right calibration file and making sure it represents the microphone. When you start looking at measurement microphones, they come in 2 varieties. The pressure one just measures the pressure response. The free field one has this correction designed into it. Between that and the calibration file, you can have some confidence that your high frequency measurement is reasonably accurate. And then here with that inexpensive natty microphone, I show you that on axis, and then I just rotated it so it was 90 degrees, and at 20 kilohertz, a 2.5 dB difference. Now in practice, that's not a whole lot. You're going to have much bigger issues with your drivers than this, but just be aware. And if you have a calibration file for the microphone, the calibration was for the microphone pointing directly at the sound source. Use it that way. Otherwise, you're just going to confuse yourself. If you have a calibration file for 90 degrees, use that and use it at 90 degrees. But don't mix them. The other thing, all of these things, we can go make all these measurements. If you make a measurement and it doesn't make sense, it's probably wrong. You really need to know what's going on, know what to expect before you go and make the measurements. If you don't know what to expect, don't trust that what you're measuring is actually accurate. It may just be an artifact of the way you measured it. You have to understand what you're doing, otherwise you're making measurements and you can spin your wheels for days. Even when you know what you're doing, I can attest to having done that. The other thing I should have mentioned there, if you have something that's known, always have it handy so you can stick it in there and verify that what you're measuring is real. It's true for all of this stuff. Amplifiers, and in this case, even impedance. This is typical, all of the software and even the hardware software package solutions will give you the ability to measure a loudspeaker's impedance. What you're doing is measuring current and voltage going through the device under test. In this case, you measure the voltage across the speaker and you have a series resistor on which you can measure the current. And then the software looks at those two and will tell you what the impedance is and what the phase angle is, or resistor, capacitor, all of that. It can calculate all of that just from this information. And the software today is really good. Follow the vendor's instructions. If you're using ARTA, do exactly what they say the way they say. And then the other thing, take a known resistor, or actually several, and test it. I once got tripped up because I had wires backwards, and instead 1 ohm measured fine, 10 ohm measured at 0.1 ohm. So you have to make sure you get them right and check it, because it's so many opportunities to get it wrong. And then also, if we're going to measure drivers for TL small, you want to measure it at very low levels, because then you're not dealing with driver parameters, you're dealing with the acoustic resonances of the system. The problem is measuring at low levels is ambient noise can degrade the quality of the measurement. So ideally, if you have a way to average a bunch of measurements to just make sure that it's accurate, that would be very helpful. Okay, acoustic tests. Let me try to illustrate it. This is it's kind of what I have here, except I did this at home, and that speaker's about 1.5 feet from the ceiling. As you can see, the direct signals are the two red, the reflection comes off the ceiling, and that takes us here. And this is the same thing I showed you earlier. The direct signal is that part. If you look at the timeline there, you can see there's about 1.5 milliseconds of clean signal. Then all the rest of this are reflections off the ceiling and all the other crap in the room. The useful information is just that front part. All the rest of this is telling you what the speaker plus all the reflections are going to give you back in terms of frequency response. Unwindowed. If you just gather all of that, you throw it in, that's not very useful. It doesn't tell you much that you can make use of. And sometimes you get this in the real world, and that's very frustrating, even with a windowed measurement. This is what happens when I just take that one window. Now, this software will go and sort of patch in a low frequency, but I wouldn't trust any of that. Notice that huge suck out, but suddenly it has full energy at 50 hertz. That's a lie. That little driver does not give you full response at 50 hertz, so don't worry about it. But as you can see, the response actually is pretty linear as these things go, because this is 2 dB per division, all the way out there to 15 kilohertz, where you run into some issues, which come from the dimensions of the tweeter housing. And you can see the phase is pretty linear up to about 2 kilohertz, which is where the crossover is, and then you start seeing a change. So then I change the delay, and see the tweeter is pretty phase linear up there, but it's not at the same time as the woofer. And as I remember, yeah, see up there where it says the delay compensation, 1.6 milliseconds? That is the delay between where the electrical went in and the acoustics got seen by the microphone. Now if we go back one, you see that it's 1.8 milliseconds. So there's 200 microseconds difference in the time delay. This is what phase matching is all about. Given the design of this, I'm surprised he didn't do a better job of correcting it. But then again, if you did correct it better, you'd run into marketing problems. And then a couple of other quick measurements from this system. This is energy versus time. This is kind of a useful thing for seeing what's happening. The initial peak, that's the signal coming off the driver. See that big thing over there? That's the reflection off the ceiling. With more effort and analysis and a cleaner set of measurements, you can also see the energy coming off of the edges of the cabinet and all kinds of things as they come through. And this helps for identifying where the problem is. If you look at the time and then you remember that sound travels basically 1 millisecond, 1 foot, it's not precise, but it's good enough to start figuring out, okay, that's a 0.5 millisecond, look for something 6 inches from the driver, and that's causing a problem. Okay, we'll get into that a little bit, but the idea here, this is the magic of FFT and inverse FFT. The drive signal in this case is a chirp. And you may have heard it earlier when I was trying to make this thing work, a quick chirp. What it does is gather all of that in, does an FFT of that to find the impulse that would generate that energy. And then it does an FFT of the impulse to get back to the frequency response. Yeah, this was derived from an impulse that was derived from an actual chirp. And this is the way it's done today. Okay, this is also a very useful thing once you understand how to pay attention to it. This is the cumulative spectral decay, waterfall plot. These are the kinds of things that people look at and try to determine a lot from it. Up here, that is the actual frequency response of the system when you measure just the frequency response. This is how much energy is coming out of it over time. This is 500 microseconds. You see there's still energy coming off of the tweeter here. Some of this is actually energy rattling around inside the cavity of the tweeter or on the cone, all of that stuff. These are the things you don't want. That up there is what you do want. And you want to spend some time understanding that. I have seen some speakers with whole bunches of energy that trail out 10 milliseconds. And that's 10 milliseconds after the sound went away. You don't want that. Now at low frequencies, I mean 100 hertz is 100 hertz would be 100 milliseconds. So of course you're going to still see energy 100 milliseconds later because we have to keep track of time versus frequency. Now let me go back here, and this is an important thing to understand. This window direct area, we got 2 milliseconds. So within 2 milliseconds, you're looking at what would be the anechoic response, pure response of the speaker, nothing else. 2 milliseconds, that's 500 hertz. Everything below 500 hertz is starting to get blended in with reflections. So you can only use that to gauge the drivers. The rest of this stuff is some mix of driver and what the room's doing with it. So keep that in mind. That's why things like the, as I was saying, the ground plane measurement, if you can do it, and the nearest thing is like 15, 20 feet away, you can actually measure low frequencies with some meaning. Otherwise, you're measuring how it's interacting with the room. Okay, that was using my familiar praxis. I spent some time trying to figure out how to do all this stuff with both ARTA and REW because they're common. You can get them for free to go play with. You should send them money if you're really going to be using it. Okay, with ARTA, I should have pulled out the main screen, but in essence, you get to this screen if you're going to go record your impulse. Took me a while to figure this out. You set it up here, you click the record button, it collects the data. Then you can get, it goes and gives you the impulse. This is the same setup with a different microphone. And you can see the impulse and sort of all of the ringing. But they have built-in software that does some windowing, but not a whole lot. You can see all the wiggles. That's because it's not windowing it as optimally as I was doing. It kind of has no choice. And there's ARTA's energy time curve. That actually looks pretty clean. But again, it gives you all of these measurements. And there's what they call a waterfall, and I can't make sense out of this at all. But this is what I'm familiar with. It's very like that other waterfall. As you can see, there's some high frequency stuff and mid-range stuff. The mid-range stuff here is probably ringing and bouncing around in the room. It's not actually from the driver, but you don't know, and this is where you really want to have that free space, a large window to do it. Now, REW will do the same thing, and okay, this is the main screen for REW. You pull it up, it gives you all of this stuff, you're very confused, as I was. You go to the measurement screen, it pulls up this, you click start and it does its record. Then you can go back and it'll give you these measurements and you can click the other buttons and you get their other plots. And again, they have a lot of interesting plots, but the real challenge with this, and this illustrates it, it's not getting the data, it's understanding it. You can get lots of data, doesn't mean anything to you because you don't know what it really means. You need to understand, in this case, relatively uniform frequency response, below 100 hertz, it rolls off. That's to be expected. That's what it should do. Except you can't make sense of that. You can go smooth it. I'd be cautious about smoothing it until I know what's causing it not to be smooth. Okay, now that you have this, you need to know, again, what to look for. Things that you can fix. You got this nice frequency response measurement. Now you want to go look at what's good, what's bad. Do you have the woofer and the tweeter in balance? Is the woofer much stronger? Is the woofer much lower? Do you have a big transition at the crossover? Do you have a region where the, say, from 2 to 4 kilohertz is up about 2 to 3 dB? You want to make that flat. Traditionally, unless you want that forward sound. In the commercial marketplace, sometimes you want that stuff because that's what sells the product. But for our purposes, you probably want it flat. You want to use this to figure out what's going on in the crossover. Because you have the phase information where you can get it, it makes it easier to see if the woofer is transitioning to the tweeter with a uniform, or if suddenly you have a complete phase flop, or you have a suck out, or anything like that. You need to know what's going on if you have the crossovers lined up and all of that. Cabinet diffraction, I was mentioning, like with the ETC, you can have a cabinet, like this one is not really great with all those sharp edges near the drivers. Every one of those edges, there's some diffraction, you'll get a secondary signal from those, and they all do degrade the sound. Tricks like putting foam on the front, felt on the front, rounded corners, they all make a difference. They may not make as pretty a cabinet, but it'll sound better. You need to understand all that stuff. Driver spacing. One of the classic mistakes is you have a tweeter here and you have a woofer here. They're crossing over at 3 kilohertz, but they're 5 wavelengths apart. So you have a real issue there at the crossover frequency. If it's 3 kilohertz, you really want them 1/3 of a foot, which is what, 4 inches apart. Otherwise, they're not in the same space. So these are the kinds of things you want to look for. You can see their effects on there if you don't have them all lined up. Typically, you want them close together so that it's the same off axis as it is on axis. Now, if you go and measure on axis, then you want to go measure frequency response off axis and see how different it is and see what it is. One of the classic issues is you have a whole lot of high frequencies off axis and then this sort of gap, and then the woofer section comes in. What that means is the room sound will actually be brighter than the direct sound of the speaker, because this room sound is missing that mid-range information, and that will affect your perception of the speaker. All of these are things that you learn about. Some of them you can't do a whole lot about. Things to not try and fix: if you have a suck out, a deep notch, leave it. You can't fix it successfully. If it's a crossover problem, put the crossover together. If it's some other kind of a notch, anything you do to put it back will degrade everything, and frankly, you'll never hear it. Actually, I built woofers for quite a few years that had a tunable notch to go match the basic room resonances, and nobody could ever set one of those by ear. You had to use an instrument because you can't hear the notch, but you can sure hear when you get rid of that room resonance. And you can't do that by ear. You have to have a generator and do it manually. Other things, if you have a driver with problems, get a new driver. You're not going to fix it with software, DSP. None of that will fix a driver that's rattling, has roll-offs, peaks, resonances. Get a better driver. It's not worth the effort. It's more of an effort if you've got to build 10,000 speakers for $20 each, but you don't. Your time's worth more than that. Okay, so now I blew through this pretty quickly. Questions? You probably have lots.
Yeah.
Let's start over at this end.
It's a pretty fundamental question. I'll try and be quick because it's not very exciting. But you mentioned about curved edges on the cabinet.
Yeah.
I was recently making a crossover in some seal cabs. First or second time I've tried to do my own crossover, so I'm not an expert. But I was trying to design a baffle step filter into the crossover to increase the bass performance.
Yeah.
It sort of worked okay, and the boxes were square and cube.
Yeah.
I'm curious as to what a curved edge might do to your. Can we do a baffle step filter? You could start with box width, right?
I'm not even sure how to translate one and the other. You'd have to go set it up, measure it, and understand
So
it.
the answer is you have to measure it.
Yeah, really, anything else, the controlling the diffraction has always helped. I've never seen a situation where it didn't make things better. It makes them more expensive, but it makes them better. Next question.
Yeah. What does that chirp signal look like? You have a waveform of it?
I could probably pull one up, but it's basically, it is a sweep, a very short
Very
sweep.
tight sweep?
It sweeps typically from like 5 or 10 hertz up to 1/2 of the sample rate. In the case that you were hearing, I think it's doing it in 500 milliseconds. So it's a very fast sweep. The idea is you generate energy across the entire spectrum. Now let me touch real quickly on that. That impulse that's derived from that That impulse, an impulse will have a spectrum of energy that goes from the duration of the impulse all the way down in frequency to DC, pretty much. That's why you use it. The problem with just using an impulse, a little pop, no energy in it below the very high frequencies, so your signal to noise ratios. So that's why we take a chirp, which has all that energy, we translate it into an impulse that would cause that, and then we go to an FFT of that impulse back to the real frequency response.
Okay, so does the software that you're using actually know the time domain of each frequency?
It derives that,
Or
yes.
does it assume that it's just all generated at once?
If it's not there, it shows you.
Oh, yeah. Okay.
Yeah, and that's a very valid thing to do. Before you go and measure speakers, just do a loopback test. You should get that one sample wide impulse, and then if you do the frequency response, you should get a straight line.
Yeah, okay.
You mentioned response level, measuring different speakers, woofers versus tweeters,
Yeah,
so on and so forth. I've been using the EQ Wizard. I found it better working with the mini, like whatever.
yeah,
I started doing sweeps. Part of the problem I ran into is they tell you to get a certain level by using a pink noise generator as part of the step, the process of setting it up.
mm-hmm.
Each time I tested a different part of an active system I was trying to figure out how to balance, I did the same part of the test over. How do I know what the response level is between my woofer and my mid or my, I'm using an open baffle woofer.
Right.
And I'm trying to blend it with a full range horn.
You got
So-
challenges.
Exactly, so to get 1 watt, 1 meter, what we understand when we read specification, do I actually measure on the output of each amplifier that has a different gain level and?
What you can do is, I mean, in that context, working with that software, if it gives you a sensitivity number, because the microphone is a known distance from the speaker, you have a sensitivity number for each driver. Then you have to go translate that sensitivity number back in through the crossovers to, with a constant signal in, have you adjusted them so that the sensitivities at the end will all be the same. Otherwise, you run the whole system through it. I wouldn't even waste it. Once you have it working, don't bother with any more of the pink noise test. Just measure the whole system and then look at the different bands to see if they are lining up. And it should be pretty obvious if they are and if you have crossover problems. But if you're doing it in a room, which you probably are, you're also going to have to deal with the whole issue of windowing and room reflections.
It does that, yeah.
And if a woofer, you're crossing it over what, 100 or 200 hertz?
Somewhere around there, somewhere between, I mean, you can, it's one of the P5, units
Yeah.
that,
Yeah, you're crossing it over low.
Yeah,
In the real world that we live in, you probably can't window that and actually know what it's doing. All you can do is sort of infer from it and just listen and adjust. That's the real challenge because, I mean, even under the best of conditions, it's really hard to measure the output of a woofer in a real room and notice the woofer and nothing else.
so should I accept and listen from my listening position? Should I try doing tests from the listening position, or should I actually,
I would do it from the listening position because ultimately that's where you are.
yeah, that's
And also that's an important thing. If you measure a speaker at 1 foot, at 3 foot, and at 10 feet, it will be different even in anechoic conditions because the driver distances are different, the radiation patterns are a little different, and you have various interference patterns. When we get up to those really high frequencies, like at 20, 30, 50 kilohertz, you move the microphone a quarter of an inch and it's completely different. I was going nuts trying to go set up to be able to calibrate till I realized that it's all mush.
Could you comment on flat frequency response versus a downward? Like, I started trying reading and learning about that.
Oh, that's the whole thing from Toole and the background. Dr. Toole did a whole bunch of testing on groups of people to gauge what they preferred. Typically, they like a slight roll-off at the top end because if it's flat, it can be a little bit hard on you. So that started becoming the Toole curve, which is like 1 or 2 dB per octave, just a gentle roll-off. And then you go on the flip side, and this is where the challenge is. people start implementing that in recording studios, and then they start cranking up the top to compensate for it. So you get into this rather ugly loop where it gets worse and worse. I understand where he was coming from. He wasn't driving for accuracy with it. He was driving for what people like to hear. Now, on the one hand, you can be absolutist and say, we want to be as faithful to the original sound as possible. And then you start running into the reality of recording real musicians and playing real instruments in a real space. You can't get there. You can do some tricks, like there are various fancy microphone things, but the reality is people are going to go record them with multiple microphones in different places and do EQ and a whole bunch of other stuff that they'll never admit to put it together. It's not got, the core is not perfect such that if you reproduce it with a perfect system, you'll get something. Accept what it is, adjust it until it sounds good to you, but if you're rolling it off, know you are. Don't pretend it's right. That's where that comes in. Oh, sure.
Yeah, I have a simplistic question.
Sure.
That's the only topic I want to ask. Anyway, you guys are all above my head, and basically, I just want to know. I have a driver, 5-inch driver with a little dent in the cone.
Yeah.
In fact, it's a LR16SN, which most of you know is an aluminum cone driver. So my question is, how much does the dome contribute to the sound? Should I throw this thing away, or is it worth keeping?
Oh, the cone? You mean the cone with a dent?
The dome is dented.
Oh, the dome has a dent.
But the cone is okay.
The problem with that is that dent will affect it because of the way the sound propagates through the surface of that. If you have a dent like that, it actually does a little bit of re-radiation because of the transition. It changes the way the energy flows through it and causes some secondary radiation. I don't know if you can hear it or not. I would be tempted, unless it's an expensive driver, to just replace it or get it reconed. If it's a really expensive driver, it's tough. I have had some success sucking out those dents, but I wouldn't recommend it. You do that when you're desperate. Yeah.
Do you have a rule of thumb for how deep or how narrow of a dip that we
Okay, if the Q is over about 4 or 5, just ignore it. You'll see a sharp notch like you get with a distortion analyzer, something 5%. You will never hear it because no tone lives in that 5% long enough for you to hear it.
Okay.
Now in real music, it starts, runs, and stops, right? And the shorter that period is, the broader its spectrum. So you'll get it even if it's mostly on top of the notch. Like if you take a distortion analyzer, set it at 1 kilohertz, you feed it 1 kilohertz tone burst, you'll see some of it on the output, even though you have a 100 dB notch right there. It's because of the nature of the math and all of that.
Regarding, you do a sweep and then
You do all that stuff. You let it do it. You don't do it.
Right. I heard a suspicious fellow suggest that, like, oh, there's some sort of weird gotchas inherent in that system. I don't know whether to believe him. Have you
Oh, as opposed to doing the traditional anechoic chamber with a slow sweep?
Maybe. I don't know.
You could encounter something strange. I never have. I can understand where under just the right circumstances, you can kind of describe it as a picket fence problem. If you have 2 picket fences and they both line up, you only see one. And another problem you have with a sampled data system, managing a sampled data system, if the samples line up, you can have garbage where the samples aren't and you'll never see it. But in practice with this stuff, I wouldn't even think that there's something that'll sneak through, or that there's something that you won't be able to measure with it. I've never encountered that, and I've tried it for years.
You mentioned using a ground plane approach to do
Yeah.
frequency measurements. Could you comment about that versus pointing your speaker up and piling a ton of
Okay, if you
Carbon
point the
pillows.
speaker up in a large space, again, you still have to have that very large space and hang a microphone up above it. That is a half-plane measurement. It's not a free space measurement because it's getting the reinforcement of all the ground plane around it. That is not how you're using your speaker. So the low frequencies are altered by that. I'll be sending a link around to everybody to the original paper, or actually I may put it on someplace where you can access it, from JBL, where they first talk about using the ground plane measurement, where they compared anechoic measurements, that what you're talking about, hanging a speaker in free space off of a crane, all of this stuff, and then go to the ground plane measurement, and it just illustrates they all end up in pretty much the same place once you understand what's going on. The nice thing about a ground plane measurement is it's so simple with today's windowed software. Doing it any other way, you run into issues. If you want to know what your speaker's doing, you can take it outside if you have a nice flat space. Concrete is preferable. Carpet, even this carpet will degrade the quality of measurement because you really have to have that full hard reflection so all of the energy gets reflected. So then the 6 foot that I was talking about, traditionally you measure a speaker at 1 meter, 3 feet. That gives you a nominal sensitivity number you work with so you can compare. When you have the ground plane, because the ground plane is reflecting 100% of the energy, you have to go out 6 feet to do the correction for the 6 dB of extra energy you're getting from the ground plane. So that's where that comes in. You have to have the microphone absolutely on the ground. It can't be 1 inch or 2 inches above.
And the incline that you showed in your diagram,
That's to get the tweeter pointed at the,
so you just want everything directly on axis to the microphone itself?
yeah, unless you want to see what the off-axis response is.
I see, so for off axis,
You just tilt it or
tilt
rotate
down
it.
or- Yeah, okay.
It's really pretty simple, yes.
So the microphone is on the surface, which means you're sort of trying to use it as a boundary mic.
Pretty much the same thing.
So your mic is not designed to be a boundary mic, though.
In this case, you're not, well, it's working as a boundary mic. It's because it's the 100% reflection, it's like it's in free space. The only difference, there may be slightly off axis. But if you look at the charts, certainly for a 1/4 inch type microphone, it's not going to make a big difference.
Are the sonic tests that you're talking about, would these be any different for a near field speaker?
No, it'd be the same thing. How you end up interpreting them and exploiting them, that would be the one issue. When you're talking about near field versus a long distance, you're measuring, if you measure at 1 meter or 2 meters like we're talking about, that's kind of a near field measurement. You go out in a real room and the speaker is 7, 8, 10 feet away from you or 15 feet away from you, then the speaker, the way the drivers blend will be a little bit different.
Okay, so for what we're talking about, it's pretty much the same.
Yeah.
Okay.
If you have problems, you'll see them in both.
Oh.
And that's really what you're looking for. Yes.
Minimum requirements for space. If you want to do a ground plane with anything, let's say.
Okay, let's work back from this. Sound travels 1 foot per millisecond. That means 10 feet, 100 millisecond, 10 feet, 10 milliseconds, that's 100 hertz. You want your reflection, if you want to measure down to 50 hertz, your reflection has to be 20 milliseconds delayed compared to the original sound. So from the speaker to the nearest reflecting surface and back has to be 20 feet roughly longer than the direct sound. That's how you sort of figure it out. That's why when I was doing it, basically this was a basketball court in a warehouse. So it went into the middle, everything was 25, 30, 40 feet away, so that meant nothing in the audible spectrum in terms of immediate reflections. But if somebody was standing 10 feet away, you could see it. All those little wiggles. But once you have that clean, it's really clean. And what was really amazing is that by using coherent averaging, if the software has it, way in the back of this warehouse was a machine busy grinding up old products. And we could basically, using coherent averaging, get rid of that. So we could really measure pretty deep. Yes.
This is a great intro. What would you recommend in terms of additional resources for us that are, reasonably well researched and helpful for us to be able to do some of this?
What I was going to do was send to the mailing list that came with this, assuming we can still access it, send what amounts to a sort of a cheat sheet with some of this information. They're going to be supplying the PowerPoint, and I'll give you a bunch of links to the places where I was stealing all these images. Yes.
You had on one of your earlier slides IM with a question mark.
IEM testing, yes. That goes back to, as he was mentioning, bandwidth limiting. What good is measuring harmonic distortion on a mid-range driver that you roll off at 2 kilohertz? Well, actually, the electrical to acoustic, you will get stuff. But in some cases, a system, I mean, you won't ever get any harmonics because it's rolled off there. And then you can do acoustic roll-offs too. I mean, there was a speaker, very expensive speaker, where literally there was no electrical crossover. It was just mechanical from a heavy driver to a light tweeter. So you won't ever get harmonics from that, but you can still get IM because the distortion mechanism is still there. It just can't generate the harmonics, but it can generate IM products. And then they would be in band. So one classic one is a swept two-tone, and then you look to see how much you get. Typically, like you'd use them 100 hertz apart, sweep them across the audio spectrum, and then monitor how much 100 hertz comes out as you sweep it across the spectrum. There are a number of tricks like that. Praxis has this interesting way of taking that chirp and generating both harmonic and IM distortion from measuring that. I haven't found that to be as meaningful as just really doing the classic distortion measurements, but it's there and it'll show you if you've got a problem. And again, we're about finding problems that we can fix. And if you want to go find problems you can't fix, it's pretty easy, but it will just be very frustrating. More questions? So I guess the next step here is that we're going to do some measurements, and amplifiers or speakers are both at the same time. How much confusion do people want? Speakers. We should measure some amplifiers as well. Are you set up to do that? Yeah. And then we can go put the measurements up on the big screen so everybody can see what's happening. You're all set up to measure your, that little, what's inside of that box?
In this box, this is just a little test amplifier, and what's really in there is the printed wiring board.
Excuse me, do we need to
Oh, I'm sorry. In this little black box is the amplifier guts of a computer speaker. So it's a crappy little amplifier. But it's easy to demo, right? If you can see the distortion easily.
Yeah.
It's an easier demo. So what we have here is the Quantasylum QA401. And this is another Quantasylum product, which is basically just a test load. So you can get no load condition, 8 ohm load, or 4 ohm load. Now one of the interesting things that they did here, for a variety of reasons, the way that this QA401 box does its thing is basically with a tone burst. It's not like the old days when we had a continuous sine wave that we swept over frequency. One of the interesting things that makes possible is that the length of that burst isn't terribly long, so that fairly small resistors can be used in the load box to test rather high powers, because you're not shooting it through there too long. And that's really a very, very nice feature.
The other thing is that the windowing is in the tone burst, not in the analysis side.
That's exactly right. This is the way this is the way you did it in the old days, right? What are these, 100 watts or 250 watts each?
Those are 250 watts each.
Yeah.
You still have to do that if you're going to do the third power testing.
That's true, that's true. But for this stuff, this is just so convenient. just that's the word for it. So now we talked about the FFT. This is a very, very simple-minded demonstration, but you can see a lot. This is a 1 kilohertz signal going into this little amplifier. Right now it's configured for an 8 ohm load. And you can see very clearly the lines of the harmonics. You know, you can see some other stuff too, and there's noise, but there's actually quite a bit of dynamic range in this. Now, right now we're operating this at 1 volt RMS coming out of this little amplifier. So, and that's not a lot. It's less than less than a watt, maybe a quarter watt, something like that.
You didn't turn on the power display. It can actually tell you how many watts.
Oh yeah, there are 1,000 things you could do with this, and I can do that in a minute. And it makes a great plot. It makes a great plot. But one of the things I want to show you here is that right now the input level is minus 20 dBV, which is 1/10 of a volt. Now this little amplifier happened to have a gain of 20 dB, so we're putting in minus 20 dBV, and we're getting out minus 0.1 dBV. So that's very close among friends. So now, if I crank this a little bit, just go right here, and with the mouse, you notice up there I'm at minus 17 now, right? And watch what happens to those lines as I crank it. See? The distortion is going up. And I'm going to push it into clipping right there. You can see that the onset of clipping is very, very sudden in these amplifiers. This is very typical. Now, I'm going to crank it back. So I cranked it back a dB and the clipping is pretty much gone. Although you could see, yeah, you can see a lot of intermod. Some people call these dirty skirts because it's stuff that's down there. It's just dirty. But now, if we go to the test load, you see that it's at 8 ohms now, right? Now, if I take the load away, you may see this distortion go down a little bit. You see some of those lines went down a little? But it didn't go back down too much. But now we're going to go back to 8 ohms. But now I'm going to switch to 4 ohms. So what we did here was I had that thing running into 8 ohms, 1 dB below clipping. So it was, you know, about as far as it could go. When I increased the load, the heaviness of the load, by going to 4 ohms, it went right into clipping because it lost some headroom. So that you could see, I mean, and again, it's very, very sudden. I think it's Class AB, yeah. It's definitely not Class D. This is an old school computer speaker. So if I go back and crank down the level, now let's go down to where we started, which was minus 20. And you can see the amplifier is better behaved. Notice up here, let's see, do I have it turned on? I don't think I have it. I'm going to turn on THD alone. Right up there, you'll see 0.035, 0.036%. And if I switch the load, it may go up a little bit. In this range, we're driving it at a low level, so it may not go up much. Oh, and I gotta move this out of the way. It went up 0.038, something like that. It's not too bad. If I had gone to a higher level, let's say we go back to, let's go back to minus 10. Okay? Now, at minus 10, we're seeing 0.043% into 4 ohms. Now, I'm thinking that if we go to 8 ohms, that 0.043 it doesn't go down much, does it? And if we go to no load, not a lot of difference. I'm a little surprised. But again, we're not pushing it too hard at minus 20 going in. One other thing, and I'm not going to go into too much detail here, but you notice that the number of harmonics is really, really high. This is not obviously, not a very particularly good amplifier. It's when you see a big spray of harmonics like that, it's kind of like crossover distortion. A lot, there's impulses going on and stuff like that. But you know, one thing I want to do here, which Demian suggested.
The harmonics that are being represented, starting from the initial highest peak, did you just count off? This is the first, second, third, fourth, fifth, sixth?
Yeah, for harmonic distortion, that's exactly right. And this is a log scale, log frequency scale. One other thing that Demian mentioned was this plot versus power. Now, Quantasylum has lots of what they call test plugins. It's a big list of different things you can do. And I'm trying to remember, was it, it was versus...
If you go up to, we're getting really involved here. If you go up to what you're displaying at the top of this panel.
Oh, that, yeah, just look for power.
It's actually not there.
Yeah, right, I see what you mean. In the DBV, right, I think it was control, yeah. See, right now it's DBV, right? We can, right, now if we tell it what the impedance is, which it, let's see, it asked for it, right? So now, if we try this, and we start it, right up there, 1.21 watts.
If you don't have your...
It's life easier when you're doing this.
That's right.
Your 8 ohm
Sometimes...
resistor isn't on it though right now, right?
Good point. I'm going to double check that. Whoop. What happened to the... I'm sorry. Yeah, I think I closed it accidentally.
To be clear, the reason for all of this is he has software that integrates the two to do all kinds of complicated stuff.
Okay, so I think this is with an 8 ohm load now, and it's reporting, let's see, where was 1.22 watts. And now if we ask it to report, let's see, I haven't tried this before, so I probably shouldn't. I was going to say, if we go back to dBV without watts, we go to volts RMS. Here's what I wanted to do. What I want to do is I'm going to crank this up to 2.83 volts.
Okay, for the display to go away and then I...
Yeah. Right. So if we crank the voltage up, you see it's at 3 volts right now. 2.8. This is close enough to 2.83 volts.
Right click where it says general one and type in the exact one you want for the generator.
Yeah, that's right. Let's see, I gotta look this way. I'm sorry.
Just so everybody understands, if you had an AP, this would be even harder to do. More windows, more panels,
That's
more
right.
confusion.
That's right.
It's just the nature of the beast.
Let's see, where's the voltage?
And if you have the traditional wall of analyzers and all of that stuff. You have different instruments you're running to do
Right.
this.
Anyway, I wanted to show one of those plots from because these test plugins are great. Let me see here. I'm going to stop this.
What's the highest voltage anchor you can test with that?
Absolutely good question. This has an attenuator built into it, and in fact that attenuator is turned on right now. It's a 20 dB attenuator. There is a limit to how much voltage you can safely put into this box, into the what we'll call the front end, where the ADC is, and it's a few volts RMS. If you want to test an amplifier that is likely at higher power levels going to produce more than that, you put in this 20 dB attenuator, and I think that gets you up to maybe 50 watts into 8 ohms, some number like that, maybe a little bit more than that. But that is a very good question, because for a lot of this equipment, you do have to have some conditioning of the output signal from the power amplifier going into the instrumentation so that the instrumentation can handle those higher voltages. If you're testing a 200 watt or a 300 watt amplifier rated at 8 ohms, you know, you're talking like 40 volts RMS kind of number.
Can't that just be a passive resistor?
It has to be a voltage divider.
It's not an $800 box.
No, well, the beauty of this, though, is this does have the 20 dB in it, okay? So, for example, yes, it does. It's switchable. You see right there. See that? I can take that out.
It's also a momentary burst, which gives you a little more headroom to be able to do that.
That's another very good point. You know, I talked about earlier when you're sine wave testing a power amplifier, the thermals can change, right? What's nice about this is that you can just do one burst and the thermals aren't going to change. And so you can see it with the bias not drifting. It'll just be what it was. So that's another advantage, in addition to the one we talked about where the load resistors don't have to be so huge as well. But one other thing that you just touched upon, which is really, it's good and bad, it's a double-edged sword, is that if you're looking for clipping, and you just do, it's basically a tone burst we're talking about here. If the amplifier is just sitting there, happy as a lark, the power supply is all charged up, right? And so you do this burst test, you're going to get much more power than that amplifier can deliver continuously into 8 ohms or 4 ohms. Because with the burst test, the power supply has not had time to sag. So there's an interesting trade-off there.
You're not really getting a real-world evaluation of what the...
Basically, that's right. That's right.
Can you simulate or initiate a set of bursts which would simulate in the right kind of order?
This
like power?
normally runs the burst at a fairly rapid rate.
Yeah.
So it's
And
not
it'll do them,
100%
yeah.
duty cycle, but it's like 20
So I'm not sure what we're
30%,
getting
I
or
think.
not getting. Sorry, so if you're getting continuous bursts, then you are getting a realistic pattern, a realistic power supply? Or?
You know, if we had a scope hooked up, and it would take time, it's probably not worth doing. But we could actually look at the burst on the scope, and you would see how long the burst lasts, and you would also see how long it is between bursts. The duty cycle, exactly right. Off the top of my head, I don't recall what the burst is.
You can actually see it if you go up to the top there and select time. It shows you the burst.
Oh yeah. Thank
Or
you.
we can plug in the scope.
Well, let's see what the time does.
If we can get it
Let's
from
see.
that and it's
We need to
useful.
run this, and then we'll look at time. There you go.
There's the burst. It tells you how long it is from 0
Now-
to 1, whatever. I don't
Right.
know what that is.
We don't know how often it's occurring unless there's something
I have never found how to change the time base.
Yeah, you know, I actually asked Matt Taylor. I used to love to test amplifiers with a tone burst generator, and I lost the tone burst generator. And so I said to Matt, I said, why don't you've got it all, you can do anything you want here, right? Once you have the A to D and the signal processing and the D to A, you've got the world by the whatever, right? So that's one of the things I had actually asked him. He hasn't implemented it yet, but I think he may. And that is, you can make this into a tone burst generator. And if you want to test an amplifier for its peak output current, that's an example of where a burst is a good thing to have available. So let's say you built an amplifier and you're advertising this as a high current amplifier, and you want to be able to boast how much current this amplifier can put into the load on a burst basis. Well, you could put a 2-cycle tone burst into there, and it's quite amazing how much current you can get out of there. It depends a lot on the specifics of the amplifier, but what you can do is you will get a large amount of current before the protection circuit realizes it, and before enough energy has gone through to pop the transistors. Yeah, this is like a transient.
You're running right now, aren't you?
Let's see, I can make sure of that.
Yeah, you are.
Yeah, it's still
Switch it
running.
over and
That's
I can
right.
Pull up the signal here.
You want the HDMI?
Yeah. We have compromised grounding here, and assuming that comes up here.
Oh, there you go.
So pretty hot. The grounding is why you see all the 60 hertz hum. I can horse around with it, but the clip leads and the terminals are not all that.
But that's the scope.
Yeah.
This is a picoscope.
Yeah, now can you go to lower sweep rate and trigger on the top of the burst?
Yeah, I think.
Yeah, 'cause it looks like it's triggering different places.
Right, right.
Oh, it's not triggering at all.
Oh, that's better.
Yeah,
That's
there
better. So it looks like we've got a 50% duty cycle.
No, it's more than that.
Well, I'd say
Well,
maybe
yeah,
60%.
60. Yeah.
It's not 100%,
Right.
but this is enough to drag down your power supply.
But I think
But not
that's a
all the way
very
down.
good point. I think with this Quantasylum, you can tell it to maybe do just one burst.
Yeah.
I think. Yeah.
The way you would do that, if you go back to the screen, if you
Mhm.
go down there, it says control space, stop it, and then hit control space and you'll get 1.
I'm going to stop it, right?
That means,
And then control space
yeah,
without a click.
just control space
Okay.
over 1 cycle. Bing.
That was
set
it.
for a single
Okay.
Yeah, because this is set to auto instead of normal.
Mm-hmm.
Let's see.
Did it-
Single.
Well, that's one way to get it. I don't even know where this.
See, I never tried that before. You learn something new every day. Control space and you get one burst.
Hit where it says stop, hit the green arrow.
No, now he has to hit it.
You ready?
one and let's hope-
Control space.
Yeah.
No, you have to hit the green arrow again because it triggered on the noise.
Yeah, I need to go set the trigger level and I have to remember
Yeah.
where to do that. There it is. Too far. There. Now if I hit that,
You ready? No?
You might,
I-
you might change it to
I
40.
don't-
yeah, it's just picking up noise.
Just-
It's not that simple to do.
Yeah.
You could try it again and maybe
Okay,
you'll catch
now?
something.
It's capturing.
This stuff is always challenging.
Yeah.
Once you learn how to use it, I don't use this very much.
Yeah. I've actually never tried to do just one burst.
Well, between doing the burst and capturing it on one of these, an hour or two from now, we'd probably be able to do a decent job.
Right. But if you give me back that HDMI, I can show you a couple of those plots that these test plugins can do. And it's really, it showcases the kind of automation that you can get from this thing. Let's see here. I'm going to go back to frequency. Oh, thank you very much. So just so we have a sanity check here. Okay, it's running again. Now I'm going to stop it. I'm going to go to one of these plugins. And just going to do this frequency response chirp plugin for a minute. And you see we have the ability to set the output level. We're going to set it at a fairly nice low level, -30. And I'm just going to hit OK and see what it does. There you go. So it just did the frequency response of this little amplifier operating at this fairly low level. Now this, see that's roll off you see up here? Right there. It's very steep, right? I believe that's the roll off of the A to D.
What sample rate are you running?
192.
That's the one. You're
And that's
hitting
80.
192 brick wall. That's not.
Yes, exactly
that's not
right.
The internal roll off. That is the.
That's the D to A or the A to D. Right, exactly right. See, this is Nyquist over 2.
Yeah. And that's why you see that.
That's
and
right.
You can make that corner sharper. A lot of trade-offs.
That's right. That's right. But what's interesting here is this this crappy little amplifier is actually flatter than the measuring system, thanks to Mr. Nyquist.
Yeah.
So but it's really neat that you can do that so quickly with that frequency response. You also notice there's some low end roll off on this. I believe in this crappy little amplifier. That's a CLA. That's a 3-letter acronym, TLA, right? Crappy little amplifier. This has probably got an electrolytic AC coupling capacitor on the output of this amplifier. And
Is it a single supply amplifier?
I don't even know.
I would bet.
I bet it is. I bet it
So if you
is.
set the impedance to 4 ohms on the load,
That's just what I was thinking of doing. So make note of where you see that curve. It's headed toward -14 at 10 hertz, right? Now we're going to put in 4 ohms. This is a real-time demo. We don't know how this is going to turn out.
Click on the other window.
I think I got to make it run. No, I'm sorry.
Now you have to stop that.
Yeah. That's right. Okay, let's try that again.
And to the existing graph, you can see the difference.
Yeah, you know, I don't see a difference, and I'm not sure why.
Well, you haven't done it yet. See where it says negative?
Oh, right there.
Click on-
Oh, sorry about that. Sorry about that. There we go.
How many audio
Success.
files does it take?
That's right. That's right. So the speculation is probably correct. The heavier loading caused the low frequency response to go down. Now let's look at another one of these plugins. I always have to remember to stop it, and it started, and I think we're okay now. Let's see. I had one down here that I kind of liked. Let's see. THD versus output power. How about that? I think that's a pretty good one. So here we have a start level of -30 dBV rather. We're going up to a higher power of -5 in increments of 5 dB. And in this case, I had it set up to do 6 kilohertz. I'm going to change that to 1.
It'd be fun to see the harmonic.
Right. Oops. All right, let's give that a try. At 10% distortion, I would say it's probably clipping.
The typical cheap amplifier is rated as
Actually,
3% or
that's
something
right.
like that.
Now, one of the things we always have to keep track of is, in addition to all of our own marbles, we have to realize, oh, wait a minute, what was the load, right? Did I leave that at 4 ohms? I think I did,
Yeah, well,
right?
I,
So let's go back to 8 ohms.
You can just click on the other screen.
Yeah. And we'll run it again. Let's see.
Just slide that down and you can access the menu.
Yeah. Okay, so if we go down here again, here we go.
It actually says 8 ohm load impedance about 4, 5.
Yeah.
Yeah, but when I ran it before, it was at 4 and it thought it was at 8. So,
Now just go ahead and run, you'll see the
Yeah.
differences.
right.
And then superimpose it there.
Okay, so now
You
it's,
got more output before it crashed.
well, actually, I think it got to more output before it crashed. I don't remember which curve is which actually. But you can see the difference. It should actually be a factor of 2, shouldn't it? You know, that's maybe 6 dB among friends. I don't know, more like 10. But anyway, you can see the point is the automation that this provides you, based on the power of the PC, is pretty great. Let me just see if there's. You have any other favorites you like there? Demian?
Well, depends on what you're
Yeah.
look at, gain and phase.
THD versus frequency.
There's so much information
Yeah.
to collect real
Oh,
fast.
here's one. Output impedance versus frequency. This is going to get us to the damping factor question.
Is the sense resistor built in to the quant?
This,
It takes advantage of the computer control over the box.
Okay.
right. Let me see here. Impedance versus frequency.
You have to somehow drag that window down to see what
Yeah.
it says. Just click on it. But, oh, it may be an
No,
issue.
I think
You
it's
don't know
an
what that
error. I think it's an error message. All right.
Near the exit. No, not there.
Right here?
Right there.
Oh, okay. I saw this morning. There's still something in the set. This is the automated version. We just uncovered. That's right. There is a different one though. Here we go. I think this one will do. So, okay, it's going to make the first pass measurement, and it's asking us to attach an 8 ohm load, which is already there. So we're going to connect. We're going to just hit OK, and it's doing a bunch of tests for us. All right. Now it's saying it's going to do another pass. Now the way that this thing infers the output impedance is it looks at the output level for 2 different loading things, and it infers the impedance. So I'm going to go back into the box. Too many windows. Okay, I'm going to hit it for 4 ohms, which is what it asked me to do.
And just click on OK.
And I'm going to click on OK. And it's doing its thing. Okay, so remember earlier I speculated that there was an electrolytic coupling capacitor in the output. And sure enough,
Not only is
the
that,
out
you can calculate its value for that. It's
That's
roughly
right.
1 ohm at, what is that, 1025 hertz?
Yeah, it's right. So it's a crappy little electrolytic capacitor. That's probably what it is. But when you do this is a different way of measuring the damping factor of the amplifier, different than the traditional way that I talked about before. This is very fast.
You'll notice that the output impedance is increasing at high frequencies because it's running out
That's
of
right.
gain.
That's right. You can see it up a little bit there.
Yeah. On this scale, it's no surprise.
That's right. Now, if we wanted to get into this more, which we probably don't have time to do, we could start the measurement frequency at 100 hertz. So the auto scaling would show us a little bit more up there. And in fact, if we wanted to, we could make the measurement go up to even a higher frequency. Right now it's set to only go up to 20 kilohertz. But the point is, what's happening up here is probably that amplifier may actually have one of those inductors in it for stability. It's also got less negative feedback up at that frequency. So it's the negative feedback is what's keeping this impedance so very low here. So when it runs out of gas on the feedback, the output impedance is going to start going up. And that's what you see the beginnings of right there. What else should we do, or should we just take questions, or what would you like to do?
We want to measure some speakers.
Yes.
Can you show us a little back operation of quantifier so that we could see the noise floor?
I'm sorry?
Can you show us the little back operation?
Back to back? Oh yeah, sure. That's easy. Now, you don't see any of the noise yet because we need to adjust the axis. So if we go to Y min, let's see, going in the wrong direction. So now we see stuff going on.
Not much. Yeah, you're only doing 16K.
That's right.
You aren't even seeing the harmonics yet.
That's right. So one of the things we may want to do is bring up the level a little bit. See, we're at minus 20. I think the sweet spot is around, what, minus 6, something like that?
No, minus 15.
Is it minus 15 where the sweet is? Okay. So we're at about minus 15 here.
Then you need to crank the FFT up.
That's right.
You have a real trade-off there. See
Oh, yeah.
in the upper corner now how many points the FFT translation is? It's 16,000.
Now I just doubled it.
Every time you double that, it's like on your frequency resolution goes up. That also means it takes a lot longer to do.
That's right. Now on top of that, I'm going to increase the averaging. Do 4x averaging. Now you're going to see this whole thing takes a lot longer.
And also, if you go much further, you run into some other bugs
Yeah.
where you can't recover.
But what you see here is increasing the FFT and doing some averaging uncovered some of the harmonics that were down there in the noise.
Look at distortion you see up there. It's about 107, 108 dB.
Yeah, which is about what it's rated at.
Yeah, I think you see the harmonics because the noise.
Yeah, you can now see the harmonics that are climbing out of the noise. That's because
Right.
of the narrow resolution. So the noise occupies less space there. Same noise, it just, you effectively push it down because it's random, but
Right.
because the harmonics are always there, they start building up and you can see them.
Okay, we're getting the time signal. Can we? What's that for?
5 more minutes.
5 more minutes
and
for
we're
what?
out of here.
We were only supposed to be here until 5 with this gentleman here, so I'm just trying to.
Okay. Let's
Other than
quickly
that-
do some speaker stuff. Can we?
I guess.
Oh, is that just
5-minute speaker test.
Yes.
And then after that we can
I have no say on that, I'm just saying.
We can measure, make more time here, but not, we can't watch it.
That's right.
Do they have to close the building or something?
Pardon me?
Do they have to close the building or something?
Well, my understanding, I'm only going based on what they told us, is this was supposed to go until 5 o'clock. So the fact that they haven't bugged us, the guys down the street there, or down the next